If you think about it, all of the graph algorithms that we've studied so far have been some kind of variation of a searching problem. So for example, find a path between two vertices, find all of the vertices in the same component as some starting point, or find all of the strongly connected components of a graph, or find a topologically sorted ordering. We have covered a few problems that are basically testing something, so test whether a graph is connected, test whether a graph is strongly connected, but even those could be argued to be a variation of a certain form of searching problem. And we know that if we go looking for something, so find a path from vertex A to vertex B, or find a spanning tree of a graph, there could be lots of different solutions. And in the algorithms that we've studied so far, it doesn't really matter which solution that we choose. So if I give you a problem like find a spanning tree of a graph, well, then a solution is any spanning tree of that graph. Or I suppose in the event that a spanning tree does not exist, reporting back that no such spanning tree exists. But we're about to transition into a set of algorithms that cover optimization. And optimization problems like this could be seen as a sort of advanced variant of certain searching problems, because one way to view these optimization problems, such as the minimum weight spanning tree problem that we're going to talk about today, are among the possible spanning trees of the graph. So go searching for spanning trees, but I want a specific spanning tree in particular. Not just any spanning tree, but a spanning tree that optimizes some condition. In this case, a minimum weight spanning tree. Now, of course, before we can really talk about that, I guess I have to define minimum and weight. And I'm going to do that by talking about this entire problem, I guess going back in time, talking about the history of the minimum weight spanning tree problem. That's going to take us back about 99 years to 1926, when a mathematician named Borůvka was studying the task of connecting a bunch of cities in southern Moravia together into an electricity network. Now, Moravia is in the modern-day country of Czechia in Europe. And maybe we can already sort of see that if I have a bunch of cities and I want to connect them together to form an electricity network, there's sort of a graph model already hiding very, very close to the surface there. That is, we know enough about graphs now to sort of understand that maybe our cities are going to become our vertices in this model, and that edges might be connections between them. There's the pairwise relationship that we usually look for as a signal that we want some kind of graph model. So Borůvka's goal was to find some way of linking together a bunch of cities such that all of the cities formed a single connected network. There it is again. So from our point of view, in 2025, this problem is already sort of screaming graph algorithms. It's sort of obvious that we want some kind of graph model. I've mentioned before that graph theory as a discipline maybe didn't come into its own until sometime around the 1950s. And yet Borůvka was studying this problem in 1926. And if we were to look at Borůvka's paper that was written after 1926, so sometime around 1926 or 1927, we would see that Borůvka indeed did model this problem as a graph. That is, the idea of a graph existed long before graph theory became its own discipline. We've already talked about that, so that goes back to the Seven Bridges of Königsberg in the 1700s, so about 200 years before this. However, if we took a look at Borůvka's paper, we would notice that most of the mathematics in it is couched heavily in linear algebra. We already know that there are a lot of linkages between graph theory and linear algebra, so in our discussion, for example, of adjacency matrices, that sort of came up. And so it's interesting to notice that although Borůvka identified this as what we would now understand to be a graph theory problem, and used some results that we could translate into modern graph theory terminology, in Borůvka's study of the problem, it was framed more as a linear algebra problem. So we can take a look at this, even at the second slide, even the most basic description of what Borůvka was looking for sort of rings a bell as far as graph theoretic properties are concerned. I want a set of links between cities. Okay, well, link obviously means edge here, and I guess city in that case must be vertex, such that all cities form a single connected network. And of course, the term network is clearly a proxy for the term graph here. And additionally, that there's no requirement for redundancy. So I don't intend to construct any suspense around this because obviously you know the title of this lecture involves spanning trees. Maybe it's already clear that what we're sort of looking for here is some kind of spanning tree of the graph. So the fact that there is no requirement for redundancy sort of gives it away. Now, in this example, we're going to assume that the links that I'm constructing, these edges, must connect a pair of cities. And this is actually a bit contrived. So if I go back here and I say, here is my set of different cities. My goal is to link them together with pairwise electrical connections such that my electricity network spans all of the different cities. Okay, I just used the word span. There is another graph theoretic term that's creeping into this discussion. You could argue that, so one way of doing this might be to connect them sort of like this. Okay, so in this case, all the cities are connected. That is, I can reach any city from any other city. I've got a spanning tree. But you could argue that in practice, what's stopping me from doing something like this? Creating a set of electrical links that all link to some location in the middle of the map. This is not a city. This is, as far as I'm concerned, the middle of nowhere. But how do I know? I couldn't just build a bunch of power lines here and then, I don't know, put a substation or something. So I don't know the electrical terminology I would need. So I am clarifying that in this modeling, we are requiring that linkages connect two cities. That is, I am not allowed to build a pairwise connection between any two things that aren't already on the map. And we could argue this might be unrealistic. I'll talk about that in a few minutes. There is a way with this model to still accommodate the idea that there could be various locations in the field that are not cities that still could be linked together. And so there's a way of adding that to our model if we need to, without really complicating the problem that much. Basically, the idea is that all of the different places that linkages could join together, all of the different places that that two different electrical connections could be linked together, have to already be on the map in advance. So we could argue, for example, that maybe vertex B isn't actually a city. It's just a location that the power company has identified as a place that needs to be connected into our network. And we could add other such locations. Whether this thing is a city or not, we need to make sure that in our modeling of the problem, everywhere that different linkages could be joined together is already on the map. It already exists as a vertex. Now, of course, there could be a variety of different options that satisfy this model with a single connected network. So I have 5 cities, and actually notice how in none of the previous slides have I drawn some base graph that I'm working from. I say I need some way of connecting these things together, and there are lots of ways of doing that, just drawing lines between things. So I've got this example here that happens to be a tree. I've got this example here. This also happens to be a tree. There could be lots of different ways of connecting all 5 cities together. So wait a minute, where does the idea of a spanning tree play into this? Because I've mentioned already, and it's clear from the title of the lecture, that we're going to be talking about spanning trees, and yet all of the examples I've shown so far are just different ways of connecting 5 vertices together into a tree. So what Borůvka wanted was a network that connects all cities with the minimum total cost. And I'm going to go out on a limb here and assume, based on my very limited understanding of the way electrical networks work, that if I chose to build high-tension power lines between city B and city D, that the cost of that would be at least $1. That is to say, the construction cost of any link should be a positive number. It shouldn't be that it's somehow free to do that, or that I get paid to build that link. That is, I actually make a profit from constructing something. So Borůvka wanted to build the network with the minimum total cost. That is, if I add up the costs of building every link, I want that number to be as small as possible. And one observation we can make about this is we can model these cities as vertices all we want, but there is some real-world implication behind building a particular link. So for example, assuming that this map is even vaguely to scale, I would imagine that it's probably relatively cheap to build a linkage between city A and city B compared to, for example, building a linkage between city B and city D, because it's both a longer span of distance, but also because apparently it crosses a body of water. And I'm no expert, but I would imagine that building a crossing of a body of water for power lines, whether that goes over or under the water, is probably more expensive than just building it over land. And so one question we can think about here is, if I have n cities, what is the minimum number of links to guarantee that I have a connected network? Or the minimum number of links such that I can create some connected network? I guess the guarantee part isn't necessary at this point. And because we already know that we're talking about trees, this is a nice, pleasant, comfortable review question, but it should already be sort of clear that the answer to it is n minus 1. We know that any tree on n vertices, and of course, vertices are cities here, it's right in the name, must have n-1 edges exactly. And earlier when we talked about those basic proofs about properties of free trees, I mentioned that this comes up all the time and that having those theorems like in any free tree on n vertices you have n-1 edges, can really help us later on, because when we find ourselves modeling problems that use trees, the minute we can identify that we're talking about trees, we get this huge compendium of different theoretical results we can drag in and use, and this is one of them. So on any n-vertex tree, you will have exactly n-1 edges. Now, the next question is, if all possible links have the same cost, how can we find a viable network? And the answer is, to be honest, we don't even need graphs at that point. So if I assume that I'm allowed to build literally any link I want, so any pair of cities I am allowed to link them together should I choose to do so, well then really all I have to do if I want a viable network is just say, let's consider the vertices in alphabetical order and just link them together, A to B, B to C, C to D, D to E. That would do the trick. If every possible link is viable. On the other hand, suppose it's the case that some links aren't allowed. Now, in Borůvka's modeling of the problem, that may or may not have been the case, because we're going to present Borůvka's original problem as one that might apply to a complete graph. That is, it is possible to link city A to city E, but maybe it's prohibitively expensive. That is, logically, if there's some way of connecting all the cities together, then I could build individual pairwise links between every city, although some of them could be very expensive. And so whether Borůvka took that into account or not is sort of irrelevant to our application, because it makes sense that we could build pairwise links between every pair of cities if we wanted to. If I wanted to avoid redundancy, but I just wanted some way of linking all cities together, I could just join all the cities together in one long path if I needed to do that. So every possible link is a pair of cities. Okay, well, logically that means that I could model the whole thing, the set of possible links as a graph, where a city is a vertex and an edge represents a possible linkage. And the idea behind doing this is, what I want to do is find a way for these solutions, so individual ways of connecting all cities with no redundancy, to be part of some larger structure. So I want to make a graph that models all possible links and then view this choice of links as a subgraph of it, which we'll discover is going to be a spanning tree of it. So there's no need to model more than one link per pair, and I want to explain why I think that. So let's take a look at vertex A and vertex E. So these two cities here. Suppose I decide that I do want to link them directly to each other. So I want there to be a set of power lines linking me between between city A and city E. Now, in real life, assuming there's some non-trivial distance between these two things, there actually could be a lot of different ways of linking them together. There could be this way here, there could be this way here, there could be this way here, there could be some direct straight line. But we know that because of the geography involved, it could be that the actual linkage between them isn't physically a straight line. It could be that it's actually cheaper to build some meandering path. But it also could be that there are multiple meandering paths that could work. That is, I could try this one, I could try this one, I could try the straight line. And so the question is, why is it that our model doesn't have to consider all of the different ways of linking any pair of cities? And the answer is, well, maybe it does. But when we finally get down to modeling the graph, we don't need to consider that. So the idea is, we know there's a way to link city A to city E. We know that we could send people out in the field to figure out the best way of doing that, and there could be multiple routes I could take. But I know that my goal at the end of the day is to choose the cheapest possible connections. And that means, should I choose to connect vertex A to vertex E, suppose there's one path that costs me $10 and one path that costs me $1,000. Well, logically, I would never choose the $1,000 option. If I wanted to link vertex A to vertex E directly, I would always choose the cheapest possible direct linkage. And so I could just boil this down to one edge between vertex A and vertex E, whose associated cost, I guess I have to associate costs with edges, but the associated cost of a particular edge would just be the cheapest of all the different ways that could exist to link those two cities together. Now, as I said earlier, in Borůvka's application, it does make sense that every possible linkage is possible. Literally, that's a tautology. But if I consider city A and city C, maybe in my eventual network it is more economical to link city A to city C indirectly. But certainly, if there is a way of linking them indirectly, there would be some path that links them directly. So I could even have a linkage like this, which means in the graph where I model all possible connections, it's reasonable to assume that I have a complete graph. That is, every connection is theoretically possible. Whether it actually makes sense to build it is a different question. So if I choose to use that modeling, where I use a graph where I have an edge between link every pair of cities that I could possibly connect together, then what I want is some connected spanning subgraph to represent my eventual electrical network. So if I build these darkened edges only, if I only build those electrical connections, then I would end up with a network that connects all cities and doesn't waste time building connections that are not necessary. So of course I can still reach vertex E from vertex B, so there's no need to build the link directly from vertex E to vertex B. Now again, under the reasonable assumption that I have built none of these linkages yet, and therefore that if I choose this network, I have to build all of these, then clearly it makes sense that they're all going to cost a non-trivial amount of money, and I want to build as few of them as possible. Borůvka's problem was find the minimum total cost of linking everything together. There's no requirement for redundancy or anything else. Just link all the cities together in a single network for as cheaply as you possibly can. This choice of network has redundancy that I don't need. So for example, if I destroy that edge there, I can still get from city A to city B. And if I destroy this edge here, I can still get between any pair of cities. In fact, actually, we can knock out quite a bit of this before we end up losing any connectivity. So because this contains cycles, I'll just go out and admit it here, because this is not a tree, it's got this redundancy that we don't necessarily need in this problem. I've mentioned before that there's tons of problems where redundancy is a good idea. That is, there actually are ways to define graphs where if I knock out any particular edge, I'm guaranteed to maintain connectivity. That's actually a relatively easy thing to do. But in this problem, I don't want that. I just want connectivity with no redundancy. So what I want to do basically is constrain my search to the different spanning trees of this graph that models all possible connections. The key thing is I want to choose a particular spanning tree that meets my criteria, that optimizes the total cost. And when we're optimizing costs that we're spending, obviously what I want to do is pay the minimum amount. I want to minimize the total cost of the spanning tree that I choose to build. And we'll notice that there's something conspicuously missing from the model at this point, which is what are the costs? That is, loosely speaking, keeping in mind that the graph itself encapsulates no geometric or geographical information. That is, it is entirely my choice that I laid out the vertices like this. There's no requirement that vertex B be this far away from vertex D or that A be close to vertex B or whatever. But we can intuitively imagine that if this does map onto real life to some extent, that is, if the geography that I've chosen here is realistic given this choice of vertices, that obviously, yeah, the link between vertex B and vertex D might cost more than the link between vertex A and vertex B. But that's not really our problem. As the people modeling this, as the algorithms people involved in this, we don't really care that much exactly what the mechanism by which the pricing is determined is. Like, it doesn't really make much of a difference to me, nor am I qualified to comment on exactly how much it costs to build a link between vertex A and vertex B, or vertex A and vertex E. We can make some educated guesses. So a guess might be, if you're building power lines up into the mountains, that's probably going to cost more than on flat land. Short spans probably cost less than long spans, and going over water probably costs a lot of money, or going underwater probably costs a lot of money, but it's not really our problem. So it makes sense that we could get that information from outside. So Borůvka's problem involved finding the spanning tree with the minimum total cost, which would be the combined cost of all the links that get built, and of course this requires us to know the cost of individual links. So we could model this using something called an edge-weighted graph. And that's in bold because I guess it's a new piece of terminology. You could even argue, there are those that might argue that this is a brand new thing. That is, we've moved from graphs up to an even more complicated abstraction called an edge-weighted graph. I am not one of those people. I do not belong to that school of thought. I think this is just an ordinary graph. That is, we can tag various parts of our graph with all sorts of interesting information. We've already seen lots of applications where we tag each vertex with certain information. I don't think that changes anything. At the end of the day, obviously having a weight attached to each edge does give us more information and more parameterization to work with our algorithms, but it doesn't really mean that we have something any more advanced than the basic simple graphs that we've been working with already. So this is called an edge-weighted graph, and an edge-weighted graph is a graph where every edge has associated with it some weight value. And the term weight has been chosen here because it's a very general term. I don't want to talk about costs because we want to make sure that this minimum weight spanning tree problem that we're discussing still applies to cases other than Borůvka's problem of working with costs. On the other hand, if we choose that our weights are represent the cost of building each link, then certainly minimizing cost is a realistic application. So the weight on each edge is the cost of building that link. And now I have enough information to think about what I really want. I want a spanning tree of this graph, that is a set of links that I actually build, that has the minimum total cost. And let's see if I can just estimate that. So it seems to me as if I don't want to build this edge with cost 15. I want to try and avoid building this edge with cost 20. Let's try building this edge with cost 11. There we go. And then we'll build this edge with cost 11. And then we'll build this edge with cost 1. And maybe I did a decent job of choosing edges that have relatively low cost. But you can see that there are cases where I might have no choice but to spend a lot of money on a particular edge because there could be some vertices. Notice how vertex E, everything connecting to vertex E costs a lot. And I suppose that might be because vertex E is up in the mountains and therefore it costs a lot to build something there. Also notice that all the links that cross this body of water seem to cost a lot as well. So I may not have a choice but to build high cost links, and there might be some cases where building the low cost links is impossible because there may be low cost links that create cycles and therefore I can't use them. But there is some way of creating a spanning tree among the various possibilities that has the minimum total cost, and that is the goal of today's application. So Borůvka's problem turned out to be an example of the minimum weight spanning tree problem. And the goal of this lecture is to cover algorithms for that problem. And eventually we're going to talk about Borůvka's solution, but for a variety of reasons, I want to hold off on that. We're going to talk about different algorithms for this problem in this lecture, and we'll discover that as we move into this phase of the course where we talk about optimization, because of the constraints that optimization problems have and a variety of other issues, we actually have to learn more than one algorithm for the task. So if you think back to the last time we covered a bunch of different algorithms for something, I guess we did cover 2 different graph traversal algorithms. That does count as something. But we also spent a lot of time talking about a whole variety of different sorting algorithms for the problem of sorting an array. And although it's certainly true that for the things that we fixate on as algorithms people, that is, we're so obsessed with running time, there are certain sorting algorithms that seem to us like the standard choice. That is, we all know that I'm a big fan of merge sort because merge sort guarantees n log n performance. And I guess heap sort does as well, but for some reason I don't care that much about heap sort. On the other hand, algorithms like quick sort and selection sort and insertion sort do have a lot of value in certain contexts, and it's important that we know about them. We don't truly understand or appreciate merge sort, nor can we in a definitive way claim that merge sort is a good choice for a particular application unless we also know about the alternatives. And the same is true about algorithms for tasks like optimization. And I guess the same is true of graph traversals. That is, you can't really argue that DFS is the best choice for a problem unless you at least know about some alternative choice, that is to say maybe BFS. Okay, so a minimum weight spanning tree of an edge-weighted undirected graph is a spanning tree whose total weight, that is to say that the sum of all the weights of edges that I choose, is minimum among all of the spanning trees of that graph. Okay, so we can abbreviate minimum weight spanning tree to this, MWST. And you will notice that that has basically the same number of syllables as just saying minimum weight spanning tree. It's also completely unpronounceable as an acronym, and so therefore I'm just going to keep saying minimum weight spanning tree for most of this lecture. So the minimum weight spanning tree of a graph is not unique, which means actually talking about the minimum weight spanning tree isn't really correct. I should instead be talking about, a minimum weight spanning tree or an MWST. You can see English is causing us some grief here. So there could be more than one spanning tree that achieves that minimum cost, because obviously I'm summing things up and there could be lots of ways of achieving the same sum, different terms that could produce the same sum. Okay, and then finally, before we move into the more theoretical discussion of algorithms, I want to talk about a couple of assumptions that we already mentioned that are important to note here, because we're now talking about applied optimization. And so I love optimization problems. That's one of my favorite areas, like one of my areas of expertise and my favorite things to talk about in an algorithms context. But what's really frustrating about optimization problems in practice is that they often don't boil down to something that's very theoretically clear. That is, in practice, problems that might seem that they can be modeled by a very theoretically clear modeling, like the minimum weight spanning tree problem, don't map onto something in real life that can be modeled as easily. So here are some assumptions that we made. First, I mentioned that we are assuming that power lines, the junctions can only occur at a vertex. So it wouldn't be valid for me to say, I've got all these cities, let's just build a substation in the middle of nowhere and link them all to that. Now, this isn't a big deal because if we're considering possible locations for substations, locations, we could always try adding vertices at those locations and seeing what happens, and then computing a minimum weight spanning tree based on that. That is actually a viable way of thinking about this. But keep that in mind, that there actually are things that I can understand based on my limited knowledge of the way power lines work. For example, the fact that, you do actually have power lines and substations in the middle of nowhere sometimes, not physically in a city, that can't really be modeled by this problem. Now, the second one is really annoying because it is something we can imagine will happen in real life that we can't really model, and that would make this problem quite a bit more difficult, which is basically this. So suppose I have a bunch of cities, here they all are, and I've modeled various linkages between them. And I decide that it costs $1 to build this, it costs $5 to build that, $7 to build this, and $10 to build this. And I guess I should add one more here. Let's do this edge here, costs $100. Okay. And then I'm like, okay, well, I can solve this problem because I'm building a spanning tree of this network, and I assume that I know the cost of each link. And also I assume that the cost of each link is just the cost of actually building that thing. So therefore they are independent. That is, it doesn't cost any less to build this one based on whether or not I build this one as well. But in real life, it doesn't generally work that way. That is, if I put out a tender to contractors to build power lines, they might make a bid that says something like, look, this is our hometown here. All of our equipment is in this city. So if you build all of the power lines attached to this city only, we'll charge you half price. So in other words, you get a discount if you build a certain combination of edges. Now, that sort of breaks the model that we just spent the last 20 minutes discussing, because the model we're discussing is that each edge is effectively independent. That is, either you build it or you don't. And whether you build it or not doesn't affect the cost of any other edge. But in real life, it's quite reasonable that you could have a case like this. That is, instead of hiring a separate contractor to build all links, you could have one contractor that says, look, if you build these links, we'll charge you less. If you build all of them, we'll give you a discount. That's really annoying. It's annoying for me because it means the problem is a bit less realistic. On the other hand, if we are the contractor, that is, if we have been told build all the links yourself, that is, we're not subcontracting or anything else, then it might just come down to pricing out the cost of each link. So although this is a problem depending on what level of the process we're in, so if we're the power company contracting out, then maybe this causes us some grief. Whereas if we are the contractor deciding which links to build, then we can, in fact, model this as the minimum weight spanning tree problem. And always, we should think about the fact that even if our optimization problem doesn't map perfectly onto a theoretical model like minimum weight spanning trees, that doesn't mean that it's a waste of time to do it. That is, it's possible that maybe the discount issue, that is, maybe the contractor says, if you build all the links adjacent to vertex B, we'll charge you less. It may be true that fully modeling that discount issue becomes very complicated, or the model becomes you need to model a problem that's a lot harder to solve. It doesn't mean that using the minimum weight spanning tree model doesn't give you good results. It does give you a way of understanding the problem and at least coming up with the most expensive version of the problem. That is, if I compute a minimum weight spanning tree assuming that all costs are independent, and a contractor shows up later and offers me a discount, well, if the discounted rate is cheaper than what I already found, I might take it. But I at least know, based on my minimum weight spanning tree, if I chose to build all links independently, what is the minimum I could pay, and then I only take some discount if it's offered if it comes to less than that. So although it's true that applied optimization problems can be quite frustrating to model theoretically because usually they don't fall into some clean and elegant model, it doesn't mean that that's useless, because when we're working with a large-scale problem, as Borůvka was, we just need a solution. And we want a solution that optimizes certain criteria, and then we can cross any other bridges we need to as they come up. So for example, discounts that we get offered, or other headaches. I mean, we know that building power lines is a lot more complicated than just choosing a set of routes. There's also the matter of actually physically building them, and what if there are cost overruns or weather or whatever. Okay, that all said, let's actually talk about some algorithms. So first, a disconnected graph has no spanning trees. And in that case, of course, there is no minimum weight spanning tree. There are a lot of ways of thinking about this. There are lots of weird theoretical extensions we could come up with here. We could argue that, well, actually, the minimum weight spanning tree, the total weight of a spanning tree of a disconnected graph is infinity or something. We're going to need to use that in a future lecture for some other purpose, that is, model the lack of a path as a path of length infinity, but we're not going to do that here. Instead, here, we're going to assume that if you would like to solve the minimum weight spanning tree problem, that you have a connected graph, because you would understand, as the user of the algorithm, that if you hand a minimum weight spanning tree algorithm a disconnected graph, it cannot be expected to give you back a reasonable answer. Now, an exercise that I do plan on assigning later is, suppose you are writing a minimum weight spanning tree algorithm like one of the algorithms that we cover today, and the graph happens to be disconnected. How can you detect that? It turns out there are pretty easy ways in the algorithms that we study to detect the fact that your graph is actually disconnected without doing an explicit connectivity test. But for our discussion of minimum weight spanning trees and our coverage of those algorithms, I'm going to just assume that our graphs are connected because disconnected graphs have no solution to this problem. On the other hand, it is true, as we know, that the components of a disconnected graph, being completely separate things, could just be treated as separate graphs. And so if I really wanted to connect, so for example, suppose I have that my country consists of 2 islands, each of which I want to connect with a power line network. Well, in that case, what I could do is just treat each island separately and solve the minimum weight spanning tree problem on that. I guess I end up here with a minimum weight spanning forest or something. Now, what this tells me is that if I have some algorithm for the minimum weight spanning tree problem, I could always create this minimum weight spanning forest by just breaking the graph up into pieces and then treating each piece as its own separate independent graph. So, in other words, what I'm building to here is the idea that I should be reasonably allowed to assume that the graph we're working with for the rest of this lecture is in fact connected. Now, there's also the question of directed graphs. And we know that a spanning tree is a tree, and we don't really understand what it means for a directed graph to have a spanning tree because it's hard to generalize the definition of a tree to directed graphs. In general, we say that trees do not exist in the directed case. There are ways that we can define things that look like trees in the directed case under tight constraints. So one example is we do acknowledge that the thing that we produce with DFS on a directed graph is a form of traversal tree. That's because the tree is so organized that we don't need to worry about things like edge directions. So the DFS tree in a directed graph has all of the directions pointing away from the root of the tree. So therefore we can treat it sort of like a rooted tree in the traditional sense, where everything just sort of goes from the top down. However, the notion of a tree, like a free tree in a graph, doesn't exist in directed graphs, and we know that connectivity is more complicated in directed graphs as well, and fortunately for us, that means that we don't really have to worry about the minimum weight spanning tree problem for directed graphs. Although there are ways of generalizing the concept to directed graphs. You could look up something called an arborescence, for example, as a way of generalizing a tree to the directed case. We are not going to consider that. All the graphs we're going to consider in this lecture will be undirected. So, we are going to consider only connected graphs and observe that because every connected graph must have a spanning tree, there must always be a minimum weight spanning tree if you're working with an edge-weighted connected graph. Okay, great. So our task that we are trying to solve in this lecture is, given a connected edge-weighted undirected graph G, find me a minimum weight spanning tree. There could be more than one. Find at least one of them. Now, just a note about edge weights. So edge weights can be anything. That is, I could even concoct these really bizarre-looking edge weights that are all some arbitrary real number. All we care about for the sake of this problem, because you actually could argue that edge weights could even be symbolic. That is to say, I could have edge weights that are like polynomials. I could have edge weights that are just arbitrary symbolic things like a triangle or a circle or something. Depending on the application of my problem, I'm allowed to tag every edge with whatever I want. Now, in this context, when we talk about minimum weight, well, I suppose that for the edge weights to be meaningful in the context of a minimum weight spanning tree, I need to be able to add them together to produce a sum, and I need that sum to be some totally ordered quantity that can be minimized. That is to say, I guess I need the edge weights to be numbers. So in this context, the edge weights can actually be any number we want. So in theory, at least, for a minimum weight spanning tree algorithm, at least among the ones we cover today, it's fine for the edge weights to be arbitrary real numbers, even irrational numbers, even things like the square root of 5. However, for our purposes, nothing really changes if I go from integers to real numbers. For our purposes, we don't want to work with all this stuff. That's going to be ridiculous. So we're going to assume in this lecture that all of our edge weights are integers. Nothing really changes for this problem if the edge weights are arbitrary real numbers, so all the algorithms still work. Be careful though, because in certain future problems involving edge-weighted graphs, some of the next few problems that we cover after this one, the results can change dramatically if the numbers aren't integers or if the numbers aren't rational numbers with certain properties. And so keep that in mind, that in general, it's not always the case that stuff we can prove about the integer case generalizes to real numbers, but that is the case for this application. Edge weights are not required to be unique. So notice how in this graph, I've set all the edge weights to be 0, 1, or -1. And in general, edge weights can be negative numbers. It turns out for the minimum weight spanning tree problem that negative edge weights don't really change anything as far as we're concerned. That is, everything still works even if your edge weights are negative, even if they are 0. You might be wondering, why would I need negative edge weights for the sake of building a power line network? And I agree, that doesn't make very much sense. And that's just a sign that depending on what problem we're trying to solve, the meaning of edge weights can vary. So if I assume that my edge weights are construction costs, well then logically it makes sense that they have to be non-negative. It doesn't make very much sense that somebody would pay me, I mean I guess they could give me a kickback or something. It doesn't make sense that somebody would pay me for the privilege of building something at their own expense. That doesn't really make any sense to me. It is possible, I guess, that there could be edges with weight 0 in the power line problem, because maybe there's already power lines between city A and city E. And I could model that is a link that already exists, by just saying this link costs 0 to construct, because you don't have to do anything to construct it. So that could be realistic in this case. And so the actual values of edge weights and the restrictions on them can vary depending on the application. And if you are working with an application where the assumptions are very strict, in some cases what that means is that you might end up with easier algorithms. So for example, if I know in advance that all of my edge weights are 0, 1, or -1, then one of the algorithms we cover later in this lecture actually becomes faster, because we'll see that there's an algorithm we cover later on that sorts the edges by weight, and that sorting takes n log n time for arbitrary edge weights. But if all of your edge weights are 0, 1, or -1, well hey, you could use bucket sort. And so that could actually speed things up. So as usual, of course, be aware of the constraints of the modeling that you're using for whatever problem you're trying to solve, because the problem we're going to solve today is the generalized minimum weight spanning tree problem. There could be specializations of it where things get easier for you. In fact, one really obvious one that we've already seen is if all of the edges have exactly the same weight, well then any spanning tree is a minimum weight spanning tree, which means you could just find a spanning tree with BFS and you'd be done with it. So in Borůvka's original electricity problem, it makes sense that we can assume edge weights are probably not going to be 0 or negative. They certainly wouldn't be negative because the weights correspond to construction costs. As I said, there is some realism behind the idea of them being 0 in cases where the link already exists, although we're not going to worry too much about that case either. Okay, so how do we generate a minimum weight spanning tree? And the way I like to cover optimization problems, just because this applies in a lot of other contexts in optimization, is I know that I want an optimal solution. So an optimal solution is a minimum weight spanning tree. But maybe I can't find a minimum weight spanning tree. Can I at least find a spanning tree with relatively low weight? And so what I'm going to talk about first is a feasible solution. So there are certain collections of edges that are they have no hope of being a good solution. So here is a collection of edges that would never be a feasible solution for the minimum weight spanning tree problem. Here we go, this collection of edges here. Okay, so notice how this collection of edges is not a tree, so it's not going to be a spanning tree of any kind, and so it contains a cycle. It's also not connected. So this is a spanning subgraph. Actually, it's not even a spanning subgraph because vertex F, as far as I know, isn't even included. I guess I'll add an edge to vertex F. So here I have a spanning subgraph with 2 components. This is not a spanning tree. This is not a feasible solution. There is no way, no matter how I assign the edge weights, that this could ever be the minimum weight spanning tree. On the other hand, suppose that I chose some spanning tree. So here's a spanning tree here. So suppose I choose this one, this spanning tree, and I look at it and say, do I know whether this is minimum or not? Well, I could go figure that out. That is, I could add up the weights of all the edges. I could go look at all the other spanning trees and decide whether this spanning tree is minimum or not. Maybe it is, maybe it isn't. But it's feasible that it could be. That is to say, this thing is a candidate to be a solution to the problem. There could be a better solution, but this spanning tree does meet the criteria. That is, it is a spanning tree, and it has some total weight that hopefully is relatively small. The way I like to cover optimization problems is say, well, I don't know how to find the best solution, an optimal solution, so I'll start by just finding a feasible solution. And once I have a feasible solution, maybe I can make it better. Maybe I can improve it to find a better feasible solution, and over time, eventually reach an optimal solution. That's a very common technique in optimization problems. We are going to see it in the other optimization problems that we solve in this course. And if you go on to take a course in formal optimization, so for example, linear programming techniques, you will see that that's a very commonly used technique there as well. So my first try to generate a minimum weight spanning tree is just generate generate a spanning tree, because that's the first step to having a minimum weight one, is just having a spanning tree. So we'll use a traversal algorithm, BFS or DFS, and just take a look at what we get. All right, so if I run BFS starting at vertex A, I end up with this spanning tree here. The total weight of the spanning tree is 45. Now the question is this spanning tree a minimum weight spanning tree? So I know it's a feasible solution. That is, there is a world in which this could be a minimum weight spanning tree. That is, depending on the weights of the graph, if all of these weights happen to be small, this would indeed be a minimum weight spanning tree. Whether this is a minimum weight spanning tree of this graph depends on whether a better spanning tree exists. So I've got one with weight 45. What I can observe, though, is if I take edge AH and I get rid of it, and I add edge BH instead, notice how I still have a spanning tree. So I've deleted one edge and then reconnected the tree by adding another edge. The edge that I deleted cost 3, and the edge that I brought in cost 2, which means I saved 1 by bringing in this edge instead. In other words, this tree here with weight 45 can't be minimum because I have a way of constructing one with smaller total weight. Okay, so that means BFS didn't help us. It doesn't surprise us, frankly, that happened, because notice that, traditional BFS doesn't even know about edge weights. BFS just traverses the graph. How could BFS be expected to find a minimum weight spanning tree if it doesn't even know what edge weights are, right? That would be pretty good luck on BFS's part. So it doesn't surprise us too much that BFS isn't able to get that minimum weight spanning tree on the first try. Okay, well, for the sake of argument, let's try DFS. So I run DFS on vertex A, and I get this thing that's basically just a path, okay? And it has total weight 42. Okay, well, that is a better job than BFS did, frankly. And remember that even after I fixed the BFS tree, so I had weight 45, I got rid of 3 and I added 2, and now I have weight 44. But even after that, DFS on its first try gets me a tree with total weight 42. That's pretty good. So now I have an even better feasible solution. Maybe there is no better solution than this, in which case this is the minimum weight spanning tree. But this is certainly a candidate. But then I notice, again, there is a way of building a better tree. So I have this tree of weight 42, but again, vertex H seems to be the center of attention here. I get rid of the edge from G to H, which disconnects the tree, and I reconnect it by adding the edge from B to H. And notice that this means I save 2, because I save 4 by deleting this edge, and I spend 2 by adding the edge BH, which means I go from a tree of weight 42 to a tree of weight 40 in total. Okay, so that means that DFS's first try didn't work either. Notice also that if we think about the tree that contains this edge but doesn't contain this edge, that doesn't look like a DFS tree. That is, when DFS arrives at vertex B, it's going to keep charging forward through the graph. It's going to end up reaching vertex H via some other route. Of course, BFS wouldn't produce this tree either, because BFS would want to travel along the edge from A to G and the edge from A to H. So the tree that I'm looking at, the one that's the best candidate I've seen so far, doesn't seem to meet the criteria to be either a DFS tree or a BFS tree, at least one rooted at vertex A. It seems to have characteristics that would apply to a lot of different traversal algorithms. It also doesn't seem to be like a BFS or DFS tree rooted at vertex B either, because if you look at the tree rooted at vertex B at this point, it doesn't fan out evenly like BFS, nor does it charge in one direction like DFS. So one option then, I guess DFS is the best lead we have so far. That is, BFS gave us a worse result than DFS. Let's assume DFS is better than BFS at this and modify it to take into account edge weights as it goes. So in other words, instead of just choosing a random edge and following it, or choosing edges according to our usual rule, where when I'm at a particular vertex, I choose the unvisited vertex with the lexicographically smallest name, so C from vertex B, D from vertex C, and so on. Instead of doing that, let's choose the edge that we follow to be the smallest weight edge to the next part of the graph, the next unvisited vertex. So I'll show that off. So let's start at vertex A and perform a DFS that among the unvisited neighbors chooses the next neighbor based on following the smallest weight edge. This is a technique called the greedy heuristic. It's one of various ways of applying a greedy heuristic. We are going to see that this particular greedy heuristic is a bit too greedy and doesn't consider the global state of the tree as well as it should. Although it turns out all of the algorithms that we cover later in this lecture actually do use a variation of a sort of greedy technique. Now, why am I calling it greedy? The idea is that I'm standing at vertex A and I just want the best possible choice right now. I don't want to consider all the other edges. I just look at these 3 edges and I choose greedily the one that appears to be the best choice from my current point of view, and I just charge along that edge here. Okay, so I walk along edge AH. There we go. And logically, it does seem as if the tree I end up with as of the end of this step does have lower total weight than the one had I gone to vertex G. I guess my hope is that by the time I get to vertex G, I've followed a sequence of vertices, a sequence of edges that doesn't require me to spend too much money. Okay, so from vertex H, I notice that the smallest weight edge leaving to an unvisited vertex has weight 2, so I follow that to vertex B. From vertex B, well, okay, there is an edge with weight 5, but that goes back to a visited vertex, so I have to ignore that. So I guess the best choice from vertex B is to go to vertex E along the edge of weight 9. From vertex E, I go to vertex F. From vertex F, I go to vertex G. And then I run out of options. Oh, no, wait, actually, I can follow this edge here. This is going to be bad news. So G only has one unvisited neighbor, and it's vertex C all the way over here. So I guess I have to follow that edge. I mean, I can't follow this edge, and I can't follow this edge, and you know how DFS is. It's not allowed to back up until all options are exhausted. So I do this. I follow to vertex C. And then from vertex C, I go to vertex D. And I realize I now have a spanning tree, so I unwind from everything, and I end up with a spanning tree with total weight 42. Now, earlier we saw that we could create a spanning tree with weight 40, so this is not a minimum weight spanning tree. So it's clearly not going to be one because we've already seen a spanning tree with lower total weight. Now, this isn't that surprising because it does seem as if the choice of edges is a bit more nuanced than what I can decide at one vertex. That is, if we think back to vertex G here, I realize that I could probably build a spanning tree with lower total weight by not using this edge. This edge seems to cost a lot. If I had followed a different path in the graph, so for example, if I'd gone from vertex B to vertex C, yeah, that price of 11 is not great, but it's way better than 14, and then I connect C to D here. And so it seems as if the problem with this is that our fundamental traversals make very local decisions. Now, obviously, the traversals do produce global stuff, like a global spanning tree, but they have to make the decision about which vertex to visit next based only on what vertex they are currently on. So the next vertex that is visited is connected to the one that they're currently on. And that may not always result in the best sequence of decisions. As I said, because if I get to vertex C from vertex G, I have to follow what turns out to be the most expensive edge in the graph. Whereas if I go searching for a better way to reach vertex C, I can do it via this thing of weight 11. It actually turns out that this thing of weight 8 would be an even better path if I wanted to go to vertex D first, as we'll see in a few slides. So it's not that surprising that DFS and BFS can't quite do the trick here. They're not quite powerful enough because they're making relatively local decisions, and it does make sense that the minimum weight spanning tree problem, that is the minimization aspect of it, relies on a pretty global property, which is the total weight of all edges together, not just the weight of which edge I choose next, leaving a particular vertex. So what do we do? So this first try has shown us that we can generate spanning trees, and that maybe if we're clever we can find a way of reducing their total weight, although even with this guided approach of DFS, where the vertex I visit at each step is chosen to be the unvisited neighbor with the smallest weight edge leading into it, that didn't seem to give me the best tree. The technique that gave me the best tree, if we skim back over all the different things that we just tried, really the best technique so far has been get a spanning tree and then look at it to decide whether I can swap edges. So I noticed, for example, that if I delete this edge and I add this one, I get a lower weight. And it seems like that might be the best technique to start with here. I start with a feasible solution, some spanning tree, and I ask the question whether I can fix it, whether I can make the total weight lower by swapping a few edges around. So the question then is, so we know this tree has total weight 42, and we know that it's not minimum. Can I fix it to create a minimum weight spanning tree by adjusting some of the edges? Now, as I said a minute ago, I fixate on this edge here, because this is, as it turns out, the highest weight edge in the entire graph. Intuitively, it seems to me as if I really want to avoid including the highest weight edge in my minimum weight spanning tree. Now, that might be unavoidable. I could make that an exercise, but I think I'll just give it away. Consider this graph here. So there is more than one spanning tree of this graph. Now suppose that this edge here has total cost, well, I don't know, to be dramatic, let's say total cost 1 million. Notice that any spanning tree of the graph has to include this edge. That's too bad. So it is possible that the highest weight edge in the graph may be in a minimum weight spanning tree. That might just be bad luck. But in this graph here, it does seem like I definitely have other options. Okay, so edge CG, which is the highest weight in the graph, is part of this spanning tree. If I can find a way of replacing CG with some other edge, that would reduce the total weight of the tree. It has to, because CG has a higher weight than any other possibility. So suppose I delete it. Suppose I delete edge CG from my spanning tree. Okay, what that's going to do is disconnect the tree. It disconnects the tree and creates two different components that I then have to reconnect. So I guess what I have to do is choose an edge that bridges between these two components to restore the property of being a spanning tree. So what are my options? Well, these three edges. These are the three edges that bridge between the two components I've created. I can choose an edge of weight 8, I can choose an edge of weight 11, and I can choose an edge of weight 14. And notice, and this is going to be critical because in a minute we're going to need to write a proof of this with only sort of symbolic diagrams to guide us, but notice with this example that I can add any of these edges. It's no big deal. Any of them will reconnect the tree, and none of them will create adverse circumstances like a cycle. It's true that certainly, obviously, my eye goes towards this one here, but all of them could be added without breaking the spanning tree. They would restore the property of being a spanning tree. They wouldn't create a cycle or do anything else. So given that all else is equal, obviously what I want to choose is the one with the lowest weight. If any of them will reconnect the tree with no consequences, of course I'm going to choose the edge with weight 8, which is edge DE. There I go. And now I have a spanning tree with total weight 36. That's the best I've seen so far by a pretty decisive margin. That is, I think the best one we previously saw had weight 40. So this seems like a good technique, and I'm beginning to get the premonition of an algorithm idea here. Okay, so is there anything else I could delete to try the same trick? So what I just did was I found an edge that I thought was a bit suspicious. I deleted it to divide the tree up into two pieces, and then I reconnected those two pieces by choosing the lowest weight bridging edge between them. Okay, so what other edges look to me as if they might cost a bit too much? How about this one? BE. BE has weight 9. Okay, so that is the heaviest edge, the highest weight edge still in the spanning tree. So let's try deleting it and see what we get. Okay, we divide the graph up into these two components, or the tree gets divided into these two components. And now I take a look at the edges that bridge between the two components, and I notice, again, I can choose any of them I want. Any of these edges will restore the property of being a spanning tree, and of course, edge GH seems like the best possibility, because I can choose any of them, so of course I'm going to choose the lowest weight one. When I do, I get a spanning tree with weight 31. And it turns out that this actually is the minimum weight spanning tree of this graph. I could repeat the process, so I could, for example, delete the highest weight edge that still exists, which happens to be this edge here, although we already saw that if I delete this, we get these two components, and we have to choose between an edge of weight 11, an edge of weight 14, and an edge of weight 8. I could try deleting the edge 7, which creates these two components, and I would actually observe that, again, 7 turns out to be the best possible choice. I could repeat this process over and over again, but nothing else would actually change. So it feels to me as if this might be the basis of an algorithm. I could just take some spanning tree, a feasible solution, and then I could keep trying deleting one edge and seeing which edge I bring back in, which bridges between the two components and restores the tree. I could just do that for every edge in the tree. I could see what happens if I delete this, and then maybe I bring this edge back in. What happens if I delete this? Well, maybe I bring this edge back in too, or maybe I find some better possibility. But if I do that for every possible edge, I should assume that when I'm done, I do in fact have a pretty good spanning tree. But is it minimum? So of course, to define that, I need some kind of a theorem. I can't just say, it seems to me as if deleting edges and then choosing the minimum weight bridging edge is going to give me the minimum weight spanning tree. The property of being minimum is a pretty strict thing, so I have to be able to prove that. So if I can formalize this bridging process, then I could design an algorithm. So we need a theorem here, and it's a theorem I'm going to call the cut property, because it involves partitioning the graph into two pieces. And you'll see that in our previous example, that is what I was doing. So every time I deleted an edge, so for example, when I deleted this edge with weight 9, I take my spanning tree and I break it into two pieces. And then, so I have a partition of vertices. I've got the stuff on this side and the stuff on this side. And my goal is to choose the thing that bridges between the two sides that has the lowest total weight. So the cut property considers, suppose I have some connected edge-weighted undirected graph, and then consider that I have some set of vertices S, and the set is non-empty. And so that partitions the graph into the things in S and the things not in S, so V of G minus S. The theorem, the cut property, is that if I divide the graph any way I want, so it actually turns out there's no requirement that the vertices in S be connected to each other or anything, just that I have a collection of vertices on the left and a collection on the right. If I divide the graph however I want, the minimum weight edge that bridges between those two pieces will be in at least one minimum weight spanning tree of the graph. At least one. So Earlier, I talked about the minimum weight spanning tree, and it's great when you're solving a problem and there is only one solution, because you can talk about the solution. The problem with the minimum weight spanning tree problem is that there could be more than one of them. There could be we could be talking about a minimum weight spanning tree, not the minimum weight spanning tree. So to be clear about how this at least one minimum weight spanning tree thing works, the issue here is that suppose I've divided my graph into two pieces. There's S, there's the rest, and there are three different edges, all with the same small weight that bridge. So that is to say, there could be lots of bridging edges, but if I think about the bridging edge with the smallest weight, there's a tie. There are three different edges, all of which share the smallest weight that bridges between the three components. The issue here is if I think about a minimum weight spanning tree, so let's just draw some tree in here. So I've got a bunch of vertices on this side, they're in a tree, and all three of these must be connected to the tree. And then same thing over here. I've got some tree that I've formed. The question is, in a minimum weight spanning tree, which of these edges could be in? Well, you realize that because both halves of the tree are connected over here, maybe I can actually just put this edge in. That's one minimum weight spanning tree. Or I could put this edge in. That's another minimum weight spanning tree. Or I could put this edge in here. And so there's a bunch of other logic behind that. That is, how do I know all of these edges could be candidates? But there are cases where that actually does hold. That is, I could have a tree over on each side, and therefore any edge would bridge between them and create a spanning tree of the result. And so if the minimum weight edge that bridges between the two halves is a tie, that is, there are multiple edges with that minimum weight, there could be a case where this specific minimum weight edge is not in every minimum weight spanning tree. That is, there could be a variety of different possibilities. Now, if you felt that was convoluted, I share that opinion, and it's going to be a bit annoying for us because we have to keep working around that possibility in the proof. Okay, so here's the proof. Suppose that S is a non-empty subset of the vertices, so non-empty proper subset. All this is saying is that both S and the rest contain at least one vertex. And one thing that you need to observe here is that, as I said, there's no restriction on the set S besides that it contains at least one vertex. That is, it's not required that the contents of S be connected to each other or anything. It's just required that I have some partition of the vertices along this line. There's stuff on the left and there's stuff on the right. And the only requirement is that there's at least one thing on the left and at least one thing on the right. Okay, so let S be some proper subset of the vertices, and suppose that the minimum weight edge, E, we'll call this edge E, with weight W, between anything in S and anything on this side, the minimum weight edge that bridges between these two pieces, is suppose that it is not in any minimum weight spanning tree of G. So of course we can see this is going to be a proof by contradiction. Now, here's an edge. We've just said that this edge is in no minimum weight spanning tree of the graph. So no minimum weight spanning tree contains this edge. Now consider some minimum weight spanning tree of the graph. We know that the graph is connected. That's part of the theorem. And therefore there needs to be a minimum weight spanning tree. So consider a minimum weight spanning tree of the graph. Because this is not contained in any minimum weight spanning tree, well, then that means that if I add this, so if I add edge E to my tree T, I'm guaranteed to produce a cycle. Obviously, because if you add any edge to a tree, you're guaranteed to produce a cycle. There's one of those tree theorems coming in handy again. So this edge is definitely not in my minimum weight spanning tree, so I add it to my minimum weight spanning tree, and that's guaranteed to produce a cycle. There has to be some way, you can sort of see it here, that I can wander all the way across. Oh, wait. Across. Well, I should be careful about that. That's the next slide. Since the cycle has to cross between two components, so basically what I'm saying, actually I shouldn't say component here. That's not really the right word. The two sets. Because it's not necessarily a connected component of the graph. Because I added this edge E and I created a cycle, well, that means that the cycle crosses this bridge. The cycle crosses over between the two halves that I've created, my set S and the other side. Because it crosses the bridge and it's a cycle, that means it has to cross again somewhere. That is, the cycle has to wrap back around. Okay, so the cycle must contain some other edge, which we'll call that edge EB with weight WB, that bridges between the two pieces. It has to, because if I have a cycle that goes in one direction, the cycle somehow has to come all the way back around. Okay, so what I'm going to do now is I'm going to try deleting this edge and adding this edge. So I added this edge to my tree T, and then I know there must be some other edge that completes the cycle across the bridge, and I'm going to delete that edge. And my claim is, if I do that, we're going to call the result T prime. So T prime is my original spanning tree T with this edge EB deleted and my other edge E added. So let that be the subgraph produced by replacing EB with E in T. Notice how I say subgraph. My goal is to show that T prime, which is the result of simply swapping this for this, my goal is to show that T prime is also a minimum weight spanning tree of the graph. Because if I can show that, then I get my contradiction, because my original assumption was that this edge is not in any minimum weight spanning tree of the graph. So my first claim is that this is a spanning tree, because notice that if I go around swapping edges, I can't guarantee that I still get a spanning tree when I'm done. All I know is that I have a subgraph. I mean, I've got a bunch of edges and vertices, so I have to prove that what I end up with is a spanning tree. Okay, so I'm claiming that my new tree T prime, or my new thing T prime, is a spanning tree. So it's both a spanning subgraph and a tree. Okay, so basically the proof, neither part of this proof is very complicated. I think the first part is more complicated than the second part. So basically it's this. What I want to show first is that T prime is connected. Okay, that's one of the criteria to be a tree. So basically what I'm going to show is that it's connected and acyclic. So here's how I know T prime is connected. Okay, so my original spanning tree, which would be this one here, which doesn't include my edge E, does include the edge EB, obviously, and it's obviously connected. It's a spanning tree, so of course it's connected. What I'm going to argue is, because adding this edge created a cycle, there has to be a way from this endpoint of E to reach the corresponding endpoint in S of EB. Similarly, there has to be a way from this endpoint, the other endpoint of E, to reach the other endpoint of EB. In other words, if I consider any two vertices in T prime, there is a way to get between them. Because, for example, in my original tree, if I chose a vertex over here and a vertex over here, there was a way to reach it by crossing this bridge. And now, if the bridge is out, I know there's a way to get from this side of the bridge all the way to the corresponding side of E, so I can cross the bridge there and then get all the way back to EB. So anything that was reachable across the bridge is still reachable with my new bridge with edge E. Okay, so therefore T prime is connected. Okay, so then the question is, I want to prove it's a spanning tree, which requires it to be a tree. I know it's connected. All I have to show now is that it has no cycles. As a spanning tree, so my original tree T had exactly this number of edges. That is a requirement of a spanning tree. So a spanning tree of an n vertex graph must have n minus 1 edges. T prime has the same number of edges as T, because I just deleted one edge and added one other edge. So it has the same number of edges, which means that it also has this number of edges. And we know that a connected graph with this number of edges cannot contain any cycles, and therefore T prime is both connected and contains no cycles, and therefore is a spanning tree. Okay, so T prime is a spanning tree. Now the question is T prime, this new tree where I use this as my bridge, is this a minimum weight spanning tree? And to reason about that, this is where I finally get the contradiction that I've been going for. So I know that T prime is a spanning tree. I'm going to show that its total weight is less than or equal to the weight that I started with. And here's why. In the theorem, we defined edge E to be the minimum weight edge bridging between the two halves of the component. Okay, it's possible, for all we know, that WB is the same weight. That is, we know that there could be multiple edges with the same weight bridging between the two halves, between the two sides of this partition. So all we know is that this weight, the weight of our edge E, is less than or equal to the weight WB. It's not necessarily less than it because there could be a tie. So what do I know? Well, I know that my new tree T prime, which does use edge E, will have total weight less than or equal to the weight of my original tree T, because I deleted this edge and I added this one. So the total weight of the tree may stay the same, but it can't go up. It either stays the same or it goes down. Okay, so now there are two cases. If the weight of T prime is equal to the weight of T, well, wait a minute. T was a minimum weight spanning tree, and T prime has the same weight, which means that both of them are minimum weight spanning trees, but that's a contradiction, because I assumed at the beginning that E, my edge E, is not contained in any minimum weight spanning tree. So clearly it is. That's a contradiction. That's case one, if the weights of both trees are equal. Now what about case 2? Case 2 is where the weight of my new tree T prime is less than the weight of my original tree T. But that's also a contradiction, because I assumed that T was a minimum weight spanning tree. But if there exists a tree with lower total weight, well then T wasn't a minimum weight spanning tree after all. That's also a contradiction. So I get a different contradiction in both cases, although there are lots of ways of breaking this down into cases. But in both cases, I'm able to show that the contradiction occurs, and therefore my original assumption has to be false. That is the assumption that E is not in any minimum weight spanning tree. Okay, so the cut property does give us the theoretical backing that we need to design our first minimum weight spanning tree algorithm. I'll call this slow minimum weight spanning tree. I start by creating any spanning tree. I create a feasible solution. Then I look at every edge in my spanning tree T, and I just see what happens if I delete it. So I take a look at the two components of T minus E. Here I can say the word component. So I mentioned there was a typo back in the proof of the cut property, because here I'm talking about some arbitrary set of vertices. Well, actually, I guess you could say these are components here because we're talking about a tree. So the key thing here is, in general, if I take a tree and delete an edge, I'm going to have two connected components left over. So I take the two components, S1 and S2, that result from me deleting the edge E. For every edge E in T, I try deleting it. I look at the components. I find the minimum weight edge that bridges back between them, and then I just swap the edge I started with in T with this new edge that I found. And I do that for every edge. So I potentially swap out every single edge in my spanning tree. This is basically the algorithm corresponding to the thing I was doing earlier, where I tried deleting an edge and then bringing in another edge that bridges between the two components that I create. So of course I can start, my initial spanning tree can be created with BFS or DFS, that is linear in the number of vertices and edges, as we know. When the input graph is connected, this is an interesting observation that we're going to need over the next hour or so. When the input graph is connected, I know that there have to be at least v-1 edges. That's a requirement of connected graphs. What that actually tells us is that the number of edges is greater than, or asymptotically greater than the number of vertices, greater than or equal to, which means that actually linear in the number of vertices and edges, well, that means that the number of edges dominates that expression. So in fact, this is actually going to be asymptotically equal to that. So that's nice because it means we can refine our analysis a bit and not worry about too many V terms floating around. So inside the loop, identifying the components, so that would be this, well, I could just do that with another traversal. That is, once I delete the edge, I could just do a traversal to figure out what components remain. And we know that a traversal that identifies all components can also be done in linear time. It is, again, we know from a previous lecture that it's actually, again, this expression here. But we know because the graph the original graph is connected, that the number of edges in the graph in total, even if I delete one of them, is going to dominate the number of vertices. And therefore, I can just assume it's big theta of E. That's why I wrote that here. Finding the minimum weight bridging edge, that would be line 5. Well, I could just do that with linear search. I could just look at every edge of the graph and figure out which ones bridge the two components, and then which ones are minimum weight among the ones that bridge the two components. So all of this, the entire contents of this loop can all be done in big theta of E time. All right, so the tree itself that I started with contains exactly this number of edges, so the loop always runs for that number of iterations. During this, I could actually replace every single edge in the tree with a different edge, but I will run for that number of iterations, n-1 iterations, which means that the entire algorithm ends up being big theta of V times E. Now, we have actually seen that expression a couple of times before. I think that came up in the context of connectivity and in maybe topological sorting, and we were able to get away from it. That is, we were able to find a faster algorithm in every previous case where V times E has shown up. Now, our luck isn't going to last forever. That is, we are eventually going to confront an algorithm whose running time really is this and is the best possible algorithm for the task that it solves, but that won't be the case today. That is, we are going to find faster algorithms for minimum weight spanning trees. Observe that in cases where I have a very dense graph, that is where the number of edges is big theta of V squared, well then this algorithm ends up being V times E, ends up actually being V cubed. And we'd like to avoid having to deal with something cubed as long as we possibly can. Although in our next optimization graph algorithm that we cover after this one, after minimum weight spanning trees, we will meet an algorithm that is V times E and is the best choice for certain applications, and we will meet an algorithm that's V cubed and is the best choice for certain applications as well. So one sign to me that this algorithm might be inefficient, that is one sign that I should keep looking, is the fact that the algorithm could spend a whole ton of time working with edges that we know would never be in a minimum weight spanning tree. I guess I should say, I should put MW here, in a minimum weight spanning tree. And basically my observation is I start with some arbitrary spanning tree, which could be full of the worst possible edges. And then I have to spend all this time finding better edges to put in. Why don't I just build the spanning spanning tree from scratch already containing good edges? Why start from an arbitrary feasible solution and then work my way up to an optimal one? Maybe there's a way, now that I've found the cut property, maybe there's a way to just get those edges to begin with. And it turns out there is. In fact, there are multiple ways of doing it, and that's going to lead us to the three main algorithms for this lecture. And so I began by talking about feasible solutions and working our way from feasible to optimal, but now using that technique, I've learned enough about the problem that I think I'm ready to start working on an algorithm to find the optimal solution directly, to build it from scratch. So the observation to make is that the cut property applies to any division of the graph into S and V minus S. I was using it in my earlier examples. I was using it in the case where I have a tree and I disconnect the tree into two components, but I don't have to. That was the reason I wanted to make that little correction in the middle of the proof. There's no requirement in general that your set S and your set V minus S be two connected components of a tree. They can just be any arbitrary collection of vertices. So for example, I could have my set S just be, let's see, A, E, and C. They could just be these three vertices here. And if S is equal to A, E, and C, and I go looking for the minimum weight edge that bridges between S, which is these three vertices, and the outside world, it's going to be the edge CD. And as we know, the edge CD is the lowest weight edge in the entire graph, and it turns out that it was in the minimum weight spanning tree that we found. Actually hold that thought, because one of the algorithms that we try involves looking at edges in ascending order of weight, on the grounds that basically the lowest weight edge in the graph is pretty much definitely going to be in the minimum weight spanning tree. And if all goes well, the highest weight edge in the graph ideally won't. If I were to set my set S to be B, E, and H, well, then the cut property tells me that edge HG must be in a minimum weight spanning tree. And we're going to have another problem with this issue of there being more than one possible solution in a minute. So you notice how it says it must be in some minimum weight spanning tree. Whether it is in the minimum weight spanning tree, we don't know, because there could be more than one of them. I believe in this graph here there is in fact just one of them, but there could be, we've seen examples of graphs where there could be lots of different possibilities. Even if I take my set S to be a single vertex, I can still apply the cut property, and I observe here that means that the edge EF must be in some minimum weight spanning tree. Okay, so we've got a bit of a logistical concern before we can continue here, which is that what the cut property is telling me is no matter what set of vertices I choose, the minimum weight edge leaving that set of vertices, so for example, I guess that would be this one in this case, is going to be in some minimum weight spanning tree. So what that tells me is basically I could just consider sets of vertices over and over and collect a bunch of edges and put them all together to get a minimum weight spanning tree, except for the fact that the cut property doesn't talk about the minimum weight spanning tree, it talks about a minimum weight spanning tree, or an MWST. So on this graph here, it happens, all edges have distinct weights. And on this graph, it is correct to talk about the minimum weight spanning tree, because there is only one of them, instead of talking about a minimum weight spanning tree, or if you want to read the acronym, an MWST. It's weird how English works. And I'll leave that as an exercise to prove that. It's not too difficult. So basically, the only reason why you might have multiple minimum weight spanning trees is that there are multiple choices for an edge. So for example, if this edge has weight 2 and this edge also has weight 2, I can see a situation where one minimum weight spanning tree might contain this to connect H to the rest of the graph, and one minimum weight spanning tree might contain that. So there's sort of a fork in the road if there's edge weights that are not distinct. But if edge weights are distinct, there is exactly one minimum weight spanning tree. Okay, so now let's just sort this whole business out about what do we do about our algorithm in the event that there's more than one possibility. So if G is a graph which has distinct edge weights, then any spanning tree T whose edges all meet the criteria of the cut property has to be a minimum weight spanning tree, because each edge in the tree, the cut property says this edge is in the minimum weight spanning tree, because there is only one of them. And that follows from the fact that you only have one spanning tree, minimum weight spanning tree, in graphs with distinct edge weights. And since any edge meeting the requirements of the cut property must be in some minimum weight spanning tree, if there is only one minimum weight spanning tree, if you find all edges where the cut property applies, you will have found the minimum weight spanning tree. The problem is that we don't know on the surface that also is the case for a graph that has multiple minimum weight spanning trees. And I guess I can describe, here's an example of a situation that might alarm me about that. So here's a graph here with a whole bunch of other edges that run off into the distance. And I've got these three edges all with weight 1. Now suppose it's the case that the cut property tells me, if I look at this as my set S, or if I look at this as my set S, or whatever, that each of these edges independently is in some minimum weight spanning tree. I can't just go through my graph and test whether each edge is in a minimum weight spanning tree and then combine what I get all together to form a spanning tree, because what if the cut property says all three of these edges each are in some minimum weight spanning tree? Well, that may be the case, but I can't put them all in the same minimum weight spanning tree because that would create a cycle. That's sort of the issue I'm dealing with here. I would never have this problem on a graph that had distinct edge weights, because I would never have a cycle like this, all of which are in some minimum weight spanning tree, because there is only one minimum weight spanning tree. So I have to write a proof of something. I'm going to call this thing the cut property construction theorem. The proof is a bit technical. That is, it's not above our level, but it's definitely a proof that exists for the sake of building a foundation. It doesn't really help us understand anything. It just puts a certain concern aside. I'm going to show the proof basically as a wall of text. I will walk through it. It's important that we have it, and I phrase it in a way that's going to help me out later, because we're going to need proofs of correctness of the algorithms that we write, and I want to avoid writing too many duplicated proofs of correctness. So I've designed this cut property construction theorem to basically tell us that if we create an algorithm that finds a minimum weight spanning tree by just going through the edges of the graph in some order, so some clever way of looking at the edges of the graph and deciding whether the cut property applies to them, if I find such a collection of edges and that collection of edges forms a spanning tree, in other words, if I take any combination of edges of the graph where the cut property tells me that each of those edges is in some minimum weight spanning tree, and I make sure that the collection of edges that I choose does not contain cycles and connects all vertices, so it is a spanning tree, then that is guaranteed to be a minimum weight spanning tree. And the algorithms that we are about to develop all basically do that. They go in some configuration, they look at the edges of the graph, and they choose a collection of those edges that forms a spanning tree where each of the edges in that spanning tree meets the criteria of the cut property. And this therefore will function as sort of an all-purpose proof of correctness of all of those algorithms. Okay, so it's phrased rather technically. Let T, that is to say my spanning tree, be this collection of edges. So I'm actually phrasing the tree as a collection of edges. We know that there's going to be n minus 1 of those edges, and I'm going to number them, and that's important for the proof. So it doesn't matter what order I number them, just assume that the edges are numbered. So let this be some collection of edges that forms a spanning tree, and the numbering of edges is arbitrary. And suppose also that the cut property applies to each edge individually. In other words, suppose that each EI is the minimum weight bridging edge between some set SI, which could be different for each edge. So in other words, for each edge, there's some set of vertices SI, such that if I look at SI on the one hand and V minus SI on the other, the edge EI is the minimum weight bridging edge between those two pieces. So what I have here is a spanning tree of edges E1, E2, E3 up to En minus 1, such that for each of those edges, there is some set, we'll call it SI, such that EI is the minimum weight bridging edge between SI and the rest. That is, the cut property tells us that EI must be in some minimum weight spanning tree. If you can create a spanning tree where every edge has that property, then you have a minimum weight spanning tree. Here's the proof. So, suppose that the tree that I'm talking about isn't a minimum weight spanning tree. Suppose that I create such a tree and it's not a minimum weight spanning tree. So what that's really saying is there is no minimum weight spanning tree that contains all of these edges, obviously, because if there were, then this would be that tree. So suppose that this isn't a minimum weight spanning tree, and therefore no minimum weight spanning tree contains all of these edges. And my next question might be, okay, fine. Is there a minimum weight spanning tree that's close? So I'll just number the edges. I'll put more numbers in here, and we'll do n minus 3, e of n minus 2, e of n minus 1. So we know that if T is not a minimum weight spanning tree, there is no minimum weight spanning tree that contains all of these edges. My next question is, fine, is there a minimum weight spanning tree that contains all of these edges, everything up to E n minus 2? Okay, what about E of n minus 3? Is there some minimum weight spanning tree that contains all of these edges? Because if there is, maybe I could complete it by fiddling around with the choices of these other two. So think about that. So think about if T isn't a minimum weight spanning tree, there has to be a minimum weight spanning tree that contains at least some of those edges, the first I of those edges. That is, in the worst case, we know by the cut property that E1 is in some minimum weight spanning tree. So in the worst case, maybe maybe if I look at the collection of edges I have here, the only sub-collection that's guaranteed to be in a minimum weight spanning tree is just E1, or it's just E1 and E2. So the proof proceeds based on that observation. So let I be the smallest number such that no minimum weight spanning tree whatsoever contains all of those edges in order, E1, or all of the edges E1, E2 up to EI. It doesn't matter what order they were numbered in, but the numbering itself was arbitrary. So consider the smallest value of I such that no minimum weight spanning tree contains all of these. Because this is the smallest value of I with that property, that implies that there is a minimum weight spanning tree that contains E1, E2, all the way up to EI minus 1. Because if there was no minimum weight spanning tree that contained all of these things, then I would not be the smallest index such that that applies. So I choose I to be the smallest index so that this entire prefix of the sequence is not contained in any minimum weight spanning tree. There's no minimum weight spanning tree that contains all of these edges. Okay, that implies that some minimum weight spanning tree, I'm going to call that M, must contain every edge up to and including E of I minus 1. All right, so now go back and consider S sub I. So we know that EI is not in, that EI is not in the minimum weight spanning tree M, because obviously M contains all of these other edges, and no minimum weight spanning tree contains every edge up to and including EI. We defined earlier that EI is an edge such that for some set S of I, EI is the minimum weight bridging edge between Si and V minus Si. So we know that EI is not in my minimum weight spanning tree M. That's the way we defined M. So there has to be some edge in M that bridges between those two things, between Si and the other side. Okay, so some edge EM, which is in M, must bridge between Si and VG minus Si. By the definition of EI, we know that EI is the minimum weight bridging edge between those two pieces. So it's reasonable to assume that the weight of EI is less than or equal to the weight of EM. So there's EM and then there's EI. Notice how this is basically just the proof of the cut property again. We're doing pretty much the same thing that we're doing there. Having this as a separate proof, though, is really helpful for later. Okay, so just like in the proof of the cut property, let's swap EI and EM in, so take the minimum weight spanning tree M, delete EM, add EI. For the same reason as we described in the cut property, in the result, which we'll call M prime, that is going to be a spanning tree, and the total weight of M prime is less than or equal to the weight of M. So here we're basically just redoing part of the proof of the cut property. Now, since M is a minimum weight spanning tree, it makes sense that there can't be a spanning tree with lower weight. So we already saw that in the proof of the cut property. So therefore, if we have to have this, the only logical option is that the weight of M prime is the same as the weight of M, which means M prime is a minimum weight spanning tree. But M prime does contain EI, and it also contains every other edge up to EI, which means that we have a contradiction of our selection of the index I, and therefore T is a minimum weight spanning tree. Okay, so that brings us to our algorithm premise, which is what I'm going to do is attempt to construct a minimum weight spanning tree from scratch by iteratively adding edges using the cut property until they form a spanning tree. Once I have some collection of edges that forms a spanning tree, and each of them is an edge to which the cut property applies, the construction theorem guarantees me that that will be a valid algorithm to produce a spanning tree, that what I end up with is a minimum weight spanning tree. Another thing I actually want to add, just as I was finishing off with that proof, there are a couple of loose ends in this proof that aren't obvious in the way that I've described it. So for example, how do we know that EM isn't one of the other things in the sequence? Just as I was flipping slides, I realized I didn't really explain that very well. So we know that we're deleting EM and adding EI, which means that if EM is one of these things, that maybe the theorem, that maybe there's some ambiguity there, maybe there's a loose end that we have to tie up. If you contemplate that case, so the proof isn't really explicitly describing this, but if you contemplate that case, EM and EI can't both be in this prefix because this prefix is part of a collection of edges that forms a spanning tree, and if EM and EI were both in that spanning tree, there would be a cycle, which doesn't make any sense. So there are some details hiding underneath the surface here because a lot of this is just recreating the proof of the cut property that may not be obvious. As I said, we have this proof mostly to put our minds at ease. This is just a rephrasing of the cut property that gives us a proof of correctness template, I guess, for our algorithm. All right, so our premise is I'm going to grow a minimum weight spanning tree from scratch by adding edges over and over again, using the cut property to find edges until I end up with a spanning tree. Now, the cut property might apply to edges that don't together form a spanning tree. So an example I gave earlier is, what if you have 3 different edges where the cut property separately says each of the edges is in a spanning tree, but you can't add them all to the same spanning tree or you create a cycle. So what we're going to do is keep adding edges using the cut property, but we're going to make sure that we always have a tree, or we always have something with no cycles at each step. So although the cut property might say that all 3 of these edges are in some minimum weight spanning tree, I would never add all 3 of them to the same one that I'm constructing because it would create cycles. If I do this, the construction theorem that we just proved would be basically a proof of correctness. Now, just to be careful, for the first of the algorithms that we cover, I will give a full proof of correctness that then cites the construction theorem. But I will make the case when the time comes that that proof of correctness is pretty perfunctory. That is really all it's doing is using some notation to say, here is how we can use the construction theorem. And then for the other 2 algorithms that I cover later in the lecture, I won't bother with a full written proof of correctness, because I think that we can see how that would follow from the proofs that we've seen in the meantime. Okay, so there's our premise, and I am now going to show 3 different solutions to the problem, 3 different ways that we could apply this, because choosing a bunch of edges that form as a spanning tree is a pretty complicated process. There's lots of ways I can do that, and I want to do that not only, I actually want to do that not only in a way that produces a minimum weight spanning tree, but I want to do it so that it's fast. I want to find some efficient way of producing that effect. Okay, here's the first idea. What I'm going to do is I'm going to maintain a tree at every step. I'm going to grow a tree outward from a single vertex V. So perhaps I start at vertex A, and I slowly grow my tree, so then it contains, let's say, vertex H, then vertex B, then vertex G. At every step I have a tree, and over time the tree slowly covers the entire graph. So I grow a single tree using the cut property to choose edges at each step until the entire graph, all the vertices are connected by my tree and I have a spanning tree. To me, this feels very intuitive because I think we are predisposed to think about an algorithm that produces a tree as having a tree along the way. That is, it makes sense if I want a tree when I'm done to start with a small tree and make it a bigger and bigger tree until I have a tree that fills the entire graph. But this isn't the only solution method, and we're going to see the next algorithm we cover after this starts with a bunch of small trees and merges them all together, and the algorithm after that does something similar as well. Okay, so suppose that I've already taken care of the vertices A, B, H, and G, as in this case here. Well, I'll just treat all of the vertices that are part of my small tree as my set S. And then I use the cut property to look at all of the edges that cross over from my tree to the outside world, and I choose the one with the lowest total weight, and that is the next thing that I add to my tree. So in this case, I would choose the edge FG. Notice that this would never create a cycle, because the edges that I'm considering are always edges that go from the tree to the outside world. And of course, the tree and the outside world are disjoint from each other, and therefore there's no way that the edge that I add connects 2 vertices that are in the tree, because one endpoint is outside of the tree, so no cycle can be created. Okay, so I add the edge FG, and that of course brings my vertex F into the set S. It's now part of the tree. So at any given point, there are the vertices in the tree and the vertices not in the tree. And the edge that I choose at each point is an edge with one end in the tree and one end out. This insight, this approach, is the basis of an algorithm that was originally discovered in 1930 by a mathematician named Jarnı, and we will call this, therefore, Jarnı's algorithm. That makes sense. Unfortunately, it doesn't make that much sense to everybody, so academic politics being in full effect, I mentioned before that one of the ways we know we're talking about intermediate graph algorithms is that things are named after people. And there's going to be some drama about that, and the biggest source of drama in my mind among all the algorithms we talk about in this course is in fact this one, because I think that there's been a bit of a travesty committed on Jarnı over the years, because this should be called Jarnı's algorithm in my opinion. That is my opinion, but other people have called it other things. Now, they've had good reasons, but it's time to fix that. It's time to fix that historical wrong. Okay, so Jarnı was actually also Czech, and Jarnı's algorithm was originally published in an article that was represented as being just a copy of a letter that Jarnı had written to Borůvka. So Borůvka already had published an algorithm to solve this problem by then. I'll cover that algorithm in a little while. And Jarnı had discovered a different algorithm for it, and had written a letter to Borůvka about it, and then published basically that letter. In fact, if you look at the title of Jarnı's article, you see this phrase here, which translates to something more or less approximating from a letter to Mr. Borůvka. And so Jarnı published basically this letter to Borůvka, and because it was in response to the paper that Borůvka had written. Now, 27 years later, so in 1957, a mathematician named Prim published this article in English. And this article proposed the same algorithm. So Prim rediscovered the algorithm and then published it. In the English-speaking world, it makes some sense that anybody who became acquainted with the algorithm probably would have become acquainted with Prim's version of the algorithm. Now, I need to be careful here and talk about what I mean by the word rediscovered, because this is something that when I first heard this story, I didn't like the look of this term rediscovered very much, especially because of the next step in the story. But it's important to understand that at that point in 1957, or whenever Prim developed this, maybe 1956, so around the mid-1950s, it does make sense that Prim would not have had access to Jarnı's article for a lot of different reasons. So geopolitics is one of them, and also because, between 1930 and 1957, to put it lightly, a lot of stuff happened in the world. And of course, Jarnı's article was published in a different language than, I assume Prim did not speak Czech, and also, unlike today, where if I want articles on a given subject, so if I go to Google Scholar or something and I type in minimum weight spanning tree, I can get all sorts of different results about articles on that subject from all over the world, including linkages of citations. So I can actually trace back chains of citations all the way into history. And these days, of course, you can actually go online and get a copy of Jarnı's article from 1930 because it's been digitized. I actually took a look at it. I found the translation of it while I was making up these slides. Things weren't that simple in 1956 or 1957. If you wanted a journal article, okay, well, first thing, you'd actually have to have the journal. You'd have to either subscribe to it or go to the library and get a copy of it. And that means there could be journals that get published in your field that you have no knowledge of because you've never heard of them before. You don't have search engines. You could ask a librarian to give you some pointers towards journals on a certain topic, but even they wouldn't know about everything. And so it does make some sense that Prim wouldn't have access to Jarnı's article or maybe know anything about it, even though there was this whole correspondence in a different language, so in Czech, between Jarnı and Borůvka that got published. Prim might not have known about it. So it does make some sense that Prim actually did discover this algorithm themselves. That is, that there was this term rediscovered isn't really a euphemism. The issue is whether Prim discovered it from scratch or not. Prim was not the first person to discover it. I mean, it was Jarnı 27 years earlier. Okay, now to add insult to injury, then this happened. So 2 years later, another article came out. This one was also in English, although it was, I think, published in a journal that was circulated more widely in Europe. So Dijkstra, who is a very famous mathematician and computer scientist, was operating in Europe at the time. And so Dijkstra rediscovered the algorithm again, and this was the part of the story where I, hearing the story as a student, was a little bit skeptical. So Dijkstra rediscovered the algorithm again and published it again, also in English. It's reasonable, I guess, that Dijkstra wasn't reading articles published in English in America or something, and therefore that Dijkstra was not familiar with Prim's publication or Jarnı's earlier publication. But this is getting sort of ridiculous. It's one thing if something gets published twice. The question I'm trying to address here is who should we name the algorithm after? Remember that I've already said that I don't consider naming an algorithm after a person to be so much an honor that we give them as simply a practical concern about the algorithm needs a name. We have to call it something, so we'll name it after the person that discovered it because it's their algorithm, the one that they proposed. It is an honor to have an algorithm named after you in the literature, but that isn't really the point. The point is just to give the algorithm a name. Okay, so what does that mean? Well, it means that somebody writing an algorithms textbook in the 1960s might have called this algorithm Prim's algorithm, because at that point, that's all that they knew about. They didn't know that Jarnı had already published it. Eventually, Jarnı's contribution became more widely known, at least in the English-speaking world, so it might be the case that all along in the area around where Jarnı operated, so in modern-day Czechia, Jarnı's algorithm might have just been called Jarnı's algorithm. But in the English-speaking world, so certainly in North America, you would probably find a lot of sources where it's called Prim's algorithm. And the people writing those sources weren't guilty of trying to erase Jarnı's contribution. They may not just have known about it. Once Jarnı's contribution became known, people tried to split the difference, and I don't consider that to be very helpful here, because if they acknowledge that Jarnı invented it, let's just call it Jarnı's algorithm. I have seen it called things like the Prim-Jarnı algorithm, the Jarnı-Prim algorithm, and even, unfortunately, because I don't think Dijkstra deserves to have this algorithm named after him, not only because he has other algorithms named after him, but because he was late to the party by, like 29 years, I've even seen it called the Dijkstra-Jarnı-Prim algorithm. And I think that that's sort of a slippery slope, because if we just give everybody a name credit every time they rediscover something, then if I rediscover an algorithm that somebody invented 100 years ago, does that mean that they add my name to it? I hope it doesn't, because that would be sort of ridiculous. And I also think that this naming is the result of some authors being sort of chronically non-confrontational. That is, even though really they should try and fix this problem, they don't want to make anybody mad, so they just keep adding more names to it to try and appease everybody. I don't think that really helps here. The textbook that I used when I was learning algorithms called it the Prim-Jarnı algorithm. And I still like that textbook in some ways. There's some parts of that textbook that I hate, but I still use it, and in fact it is sitting to my left right now. It is one of the stack of books I've been using for the past few months while preparing these lectures. But I consider this to be a serious problem. If we're going to give Jarnı an acknowledgement, why does Jarnı come second? Alphabetically, Jarnı comes first. Jarnı also was the inventor of the algorithm 27 years before Prim approached the problem, so why is Prim's name first? It makes no sense. And the more I thought about that, the more I realized that even this compromise doesn't make any sense. We should just be calling it Jarnı's algorithm. And so, thank you for listening to my long tirade, but because Jarnı published this so long before everybody else, we're going to call it Jarnı's algorithm. Now, if we think about other cases where algorithms are named after people, and two different people or a group of people discover it separately in the span of a couple of years, then maybe they could all get their name on it. But in Jarnı's case, it was decades, so it's Jarnı's algorithm. Anyway, let's run Jarnı's algorithm. So the task is run Jarnı's algorithm starting at vertex A. So the idea is at each step of Jarnı's algorithm, there's some collection of vertices that corresponds to our current working tree. At first, it's just one vertex. And then I add one vertex per step. I bring in another vertex from the outside world until the entire vertex set of the graph is part of my tree, and I actually have a spanning tree. Okay, so I'm going to run Jarnı's algorithm starting at vertex A. So currently my tree is just vertex A. I will outline the current contents of the tree in green as we've been seeing, and currently it contains one vertex and no edges. Okay, step one. The best edge between the current tree, which is just vertex A, and the rest of the graph is the edge AH, because that's the lowest weight edge joining the tree to the outside world. So we bring vertex H into the tree along this edge. Great, now the tree is just A and H. And so the tree expands and the process repeats. At the next step, the best possible edge between the tree and the outside world is edge BH. So I add vertex B to the tree. The best edge between the tree and the outside world is GH. There we go. Then it's FG, then it's EF, then it's DE, and then it's CD. Great, so I've added everything to the tree. The total weight, once I'm done, is 31. And we saw earlier that that does seem to be the minimum weight spanning tree of the graph. Bringing in any of the remaining edges and swapping them would produce a tree with larger weight. So that's Jarnı's algorithm. At each step, we have a small tree, and our goal is to expand it by one vertex, and we bring in the vertex linked along the edge that is the minimum weight edge between the tree and the rest of the world. Okay, here is a longer example. I'm going to just do a sort of flyover of this example. This is in the slides so that you have another example to work from if you want to review later. There are a couple of points. I'm going to do this long example for all three of the algorithms that we're about to cover, but I'm not going to spend much time on it. So I'm just going to flip through it for Jarnı's algorithm. So we'll start it at this arbitrary vertex G in the middle of the graph and watch as the tree grows. What I will observe about this graph is that it does have duplicate edge weights. So there's two vertices with edge weight 5. For example. What that tells me is that there could be more than one minimum weight spanning tree. I don't know that that's the case. There may not be, but there could be. And so keep in mind that there could be places that you run Jarnı's algorithm on this graph where you actually get a different result than I'm going to get here. Okay, so we add the edge BG, we add CB, I'll just keep flipping through this, and we can see the tree is now growing, sort of spreading outwards from our initial starting point, and at each step we are bringing in one vertex along the minimum weight edge linking the tree to the rest of the world. And over time we create the entire tree, and eventually we end up with our minimum weight spanning tree with total weight 101. Now, one thing I'll observe about this is that computing a total weight, like on paper or something, is a bit of a pain. Like you actually have to add those things up. But it's true that if I stop at any point in this, performing the algorithm on paper, that is, if you know what's in the tree and what isn't, it is pretty easy to find the minimum weight edge. You just consider all of the edges to vertices outside of the tree from vertices inside the tree and choose the minimum weight one. So although there are a lot of numbers flying around here, it isn't too difficult to run this kind of algorithm on paper. Okay, so when we're done, we have this minimum weight spanning tree with total weight 101. And now our question, I suppose, is how do we implement this? I'm going to show this basic high-level implementation and write the proof of correctness that I was talking about earlier. And then we have to talk about how do we make this fast, because we're going to discover that this basic implementation is no faster than our original approach, our slow algorithm. So here what I'll do is I'll store the set of edges and vertices in my tree using these two sets, which we could represent with a variety of different methods. And of course, the purpose of this is just to have a representation for now. We'll talk about how to do it fast in a minute. And then the goal here is you give me some starting vertex, who cares what it is, but I suppose it's your choice, just like with a traversal. And so I add that to my set of tree vertices. I will proceed as long as the number of tree vertices is less than the number of vertices in the graph. So I'll keep going until every vertex in the graph is part of my tree. Now, that's the most intuitive loop condition to me, but we know that, when we're done, we're going to have a spanning tree which contains exactly n-1 edges on a graph with n vertices, so we could actually use this as our loop condition. That would work fine as well. Okay, so inside the loop, at each step, as long as the number of vertices in the tree is less than the total number of vertices in the graph, I go and find the minimum weight edge with exactly one endpoint in the tree vertex set, so only one of the two vertices is in the tree. I've drawn the edge as an ordered pair here, but this is an undirected graph. This is mostly just a notational. It's just because it looks weird to draw it with set notation, or to draw it as like UV or something, because that looks like one variable name. Okay, so I find that minimum weight edge, and if we're just trying to do this in any way, we could just use linear search. That is, there probably are faster ways to do it. Spoiler, there are. But if I want the minimum weight edge, I could just iterate over every single edge and go looking. Okay, so I iterate over every single edge. That feels wasteful, but it does get the job done. And then the rest of the loop body, so that is, add the edge to my collection of tree edges, add the two vertices at either end of my edge to the collection of tree vertices, those are linear at worst. That is, linear the number of vertices or the number of edges. Because I haven't described how I implement this set, but even if I do it with a linear sequence of some kind, I could add this without creating duplicates pretty quickly. Adding u and v, here I've taken advantage of the fact that I have a set, because we know that at least one of u and v is not in the tree, but only one. So the other one is in the tree. I can add them both to my tree vertex set because it's a set. So one of them's already in there, but I can add it again without any duplicates occurring. So wait a minute. So that means the total running time of my algorithm is actually going to be v times e again, because this is all linear in the number of edges at worst, and this number of iterations of this loop is just the number of vertices. So it's actually this number in total. The total running time of the algorithm is v times e. But we know that v times e was the running time of our earlier basic algorithm. And so in the interest of trying to say something nice about this implementation, I could at least observe that this does have less overhead because I don't have to create a spanning tree before I start. So I guess it's an improvement in that sense. Now, in a minute, we're going to talk about faster implementations of Jarnı's algorithm. This is sufficient. This models the behavior enough that I can write the proof of correctness I was talking about earlier. Okay, so the first claim I want to make is that the edge set produced by Jarnı's algorithm is a spanning tree. And that's a pretty easy claim to justify because the edge that I add at each step has exactly one endpoint in the tree and one endpoint outside the tree. The only way I could create a cycle is by adding an edge between two things that are already in the tree. So if a cycle shows up, well, maybe I create a few edges of that cycle by adding stuff from outside the tree, but eventually to complete the cycle, if there's going to be a cycle that results, I'm going to have to add an edge between two things that are currently in my tree. And that's never going to happen with Jarnı's algorithm. It's impossible to create a cycle if every time I add an edge, only one endpoint is currently in the tree, because that final edge in the cycle would have to have both endpoints in the tree, and of course the algorithm doesn't do that. Additionally, the number of edges I end up with is size of v minus 1. And we know that any collection of v minus 1 edges with no cycles must be a spanning tree, because in a graph with this number of vertices, any collection of this number of edges that does not have cycles must be connected. And so it's a spanning subgraph that's connected and has no cycles. It must be a spanning tree. Okay, that's one claim along the way to our proof of correctness, and then the proof itself is just this. So the theorem is that Jarnı's algorithm does produce a minimum weight spanning tree when you start it on a connected graph. So we know it produces a spanning tree. All we have to show is that the spanning tree it produces is a minimum weight spanning tree. And to do this, I'm going to use the construction theorem, the cut property construction theorem. So the edge that I select at each step is the minimum weight edge with exactly one endpoint in the tree and one endpoint out of the tree. And therefore, I could argue that the collection of vertices in the tree, so if I need to use the cut property and I want my set S and my set S or V minus S, well then I just say, in this case, interpret the set S to be tree vertices, the set of vertices currently in the tree. And then I'm choosing an edge between that and the rest of the graph, which means the edge that I choose at each step, which is the lowest weight edge between the tree and the rest, meets the criteria of the cut property. So, Jarnı's algorithm builds a collection of edges that forms a spanning tree where every edge in the collection meets the criteria of the cut property. Those are the conditions of the cut property construction theorem. So that means that the tree I end up with is a minimum weight spanning tree. Now, looking back over these past two slides, these two things comprise a proof of correctness of Jarnı's algorithm. Basically what they do is they offload most of the heavy lifting onto the cut property construction theorem. All I really have to show is that I do not add any cycles, which is relatively easy to show, and in the next two algorithms it's going to be equally as easy to show. The proof is pretty much the same, and then I just have to demonstrate that what I do at each step to choose an edge meets the criteria of the cut property. Because of this, I am not going to bother writing out the full theorem containing a proof of correctness for the next two algorithms because it's going to be the same, pretty much the same deal. The cut property construction theorem really is the kernel of that proof. The rest of it is just adapting the algorithm, the machinery of the algorithm, to explain how the conditions of the cut property construction theorem are met. Now, before we talk about any other algorithms, let's find a way of implementing Jarnı's algorithm quickly. So as usual, when we have an algorithm that might be too slow, the question we should ask is, what exactly about this makes you feel like it's too slow? What feels like it's a bit inefficient? And to me, this jumps out at me. So if I want to find the minimum weight edge with exactly one endpoint in my collection of tree vertices, the option I proposed a few minutes ago was just use linear search. Look at every edge in the graph. So if I have my tree over here, and I want to consider, so there's the tree, and I want to find the minimum weight bridging edge, I could just iterate over every edge in the graph and only look at the ones that bridge. But the problem is I'm also iterating over all these edges in the tree, which are irrelevant to me at this point, and lots of edges that just connect to other vertices that are outside the tree, which are also irrelevant. I want to avoid inaccessible or redundant edges, edges that are already in the tree, edges that are completely outside of the tree. And it feels to me, therefore, as if I could do something to speed this up. So an observation I can make, suppose my tree is this at this moment. It's pretty clear to me that there's no way vertex G is getting brought in at the next step, because vertex G is far away from the tree. Additionally, obviously the edge AC is irrelevant because I've already brought edge AC in. The only edges I care about are these ones, the ones that directly connect the tree to the rest of the world. Okay, but we knew that. The observation I can make is, suppose I decide to bring in vertex D. So that means that this becomes a tree edge here. Okay. So this is a tree edge, and I bring in vertex D. So now my tree contains vertex D. Notice that these two edges are still candidates. For my next step, the one after I bring in vertex D, so that's be this step here, now the candidate edges are this edge, and edges that are directly connected to vertex D. In other words, the set of candidate vertices to bring in, so E, F, and H, that is determined based on what was a candidate vertex before. So before I added vertex D, these are the two candidates for things to bring in. And the edges I can bring them in on are these four edges, the edges linking these two candidate vertices to the tree. When I bring in vertex D, vertex E remains a candidate because it is still an option to bring in vertex E next, and the new candidates are just the neighbors of vertex D. It's pretty methodical. The set of edges I need to consider is whatever edges I was already considering, in other words, the status of vertex E, plus edges that connect the new vertex D to things directly outside of the tree. Vertex G is still off the table. So what I realize here is that I actually can focus my search pretty tightly. The only edges I care about are the ones that I already know about, the ones from a previous step that I never used, or the ones that I brought in directly incident to the vertex that just became part of the tree. So after I add vertex H, which is the next step after vertex D, then vertex F and vertex G are both candidates. Vertex F was already a candidate. Vertex G becomes a candidate because it's attached to the vertex that I just brought in. So I guess my idea here is what I can do is track which vertices are candidates. And then I track for every candidate the lowest weight edge that currently links that candidate to the rest of the graph. So notice even way back in this step here, at this stage, D and E are both candidates. And for vertex D, if I were to bring vertex D in, it would obviously be along this edge here, because this is the lowest weight edge connecting vertex D to the tree. If I bring vertex E in, it would be along this edge here. Okay, but then I bring in vertex D. Notice how the edge that I would bring in vertex E along is the same as it was before. And if it changes, the only way it can change is if vertex E happens to be connected to vertex D by a lower weight edge. So the mechanics of these candidates and how they interact with the tree are actually quite predictable, and it's something we can change methodically as we go through the graph. We do not need to do linear search over all vertices to figure this out. We can just save that information between steps. So I want to track the set of candidates at each step along with the lowest weight edge that connects each candidate to the tree. And I just update the candidates after each insertion into the tree. So to do this, what I'll do is I'll associate a weight with every vertex. And the weight of a vertex corresponds to the minimum weight of an edge that you can use to bring that vertex in. So at this stage here, vertex E would have weight 7, because there is a way to bring vertex E directly into the tree along an edge of weight 7. On the other hand, let's say if we look back at this step, so here vertex D would have weight 4, vertex E would have weight 7, but vertex H cannot be brought directly into the tree at this step. So we'll say that it has weight infinity. That is, it is impossible to bring it in. So every vertex gets a weight, and that is the minimum weight along which I could bring the vertex, of an edge along which I could bring a vertex into the graph. The other thing I need to keep track of is, suppose I do bring vertex E into the graph. How would I do that? Well, I'd bring it in along the edge EB. So I guess vertex B is special here. It gets to be E's tree neighbor. It is the vertex in the tree that connects that vertex along the best edge to bring it into the tree. So I want to track those two pieces of information. The weight of the vertex, which is the weight of the minimum weight edge that connects that vertex to the tree, along with its tree neighbor, which is the vertex at the other end of that minimum weight edge. As usual, here I go putting a table in the slides that maps vertices to things. As usual, remember, this is a tradition in every lecture these days, that I choose to use a table because that's good for slides, and maybe it makes it easy for us to understand, versus just having a bunch of vertices tagged with stuff, which gets really cluttered after a while. Remember that there are tons of different ways to attach a piece of information to each vertex, such that you can retrieve that information in constant time. So there's lots of ways of doing it. A table often does actually work. If our vertices are numbered with integers, consecutive integers, then I could just use a table, but I could also associate the weight and the tree neighbor with the vertex object or something else. So the fact that I use a table doesn't imply that you have to use a table. There are plenty of constant time options for looking up these properties of each vertex. Okay, so when a new vertex is added to the tree, I will update the table based on the neighbors of that vertex. And I'll show this off in a minute because I know this is a bit of an abstract statement. If an edge UV to a non-tree vertex has a weight lower than the current weight of that vertex, then the vertex U becomes its tree neighbor. And I'll sketch this and then we'll go through the example. So basically, the idea here is suppose that I've just added vertex C. Well, at that point, and let's say vertex C is my starting point. If I've just added vertex C, then I can observe that, let's look only at vertex E here. Well, then the weight of vertex E becomes 11 because there's a way of bringing vertex E in along this edge of weight 11. The tree neighbor is vertex C because the edge of weight 11 connects vertex E to vertex C. Notice that if I want to know how to bring E into the tree, it's along the edge of E and the tree neighbor of E. Okay, so now suppose that I bring in vertex B. Okay, so now the tree contains vertex B as well. So I just added the edge from C to B. Notice that once vertex B is in the tree, I want to look at the neighbors of vertex B to see whether anything has changed. And I notice that if I look at the neighbors of vertex B, I see I can get to vertex E via an edge of weight 7. So what this is saying, this last sentence here, is that once I've added vertex B to my tree, I'm going to go over to vertex E and say now the weight of vertex E is 7 and its tree neighbor is B because I just found a better edge to bring in vertex E. That's the idea. That's the update I want to perform at each step. And the update I perform, the number of updates I perform is just equal to the number of neighbors of the vertex I just brought in. Okay, so we'll do the same example as earlier where we start at vertex A, and then we'll just walk through the tree and see what changes at each step. So I bring in vertex A, and then that means that the weight and tree neighbor are irrelevant because vertex A is now in the tree, so I'll never need those pieces of information again. When I bring in vertex A, I update the entries of the table for B, C, and D because those are the neighbors of vertex A, and they are the best way to get into the tree for those three vertices at the moment because the only things that connect vertex C, B, and D into the tree are edges to vertex A. So the weight of vertex C, for example, is 2, and the tree neighbor is A, because you can get from C to the tree by the lowest weight edge of weight 2, and you end up on vertex A. Okay, so there we have that. And then at each step, if I want to choose the next thing to add, I go find the vertex with the minimum weight. That's going to be vertex C. So that tells me I want to bring vertex C in, and I bring it in along the edge AC. Okay, so I add vertex C to the tree, edge AC is added to my tree, and then C becomes part of the tree. Now when C becomes part of the tree, the table entries for it become irrelevant. I visit all of the neighbors of vertex C, and notice that before I added C, for vertex B, the weight was 3 and the tree neighbor was A, because I've got this edge here. After I add vertex C, I discover that along this edge, I can reach B by a lower weight edge. So the weight is lower along the edge BC, so I set the weight to 1 and the tree neighbor becomes C. Previously, E was inaccessible. It had weight infinity. But now I can access vertex E via this edge of weight 11, and so the weight becomes 11 and the tree neighbor becomes C. Okay, so I've added C to the tree, and then I add B to the tree, and I go and update the neighbors of vertex B. That lowers the weight of E to 7, and the tree neighbor becomes B. Okay, then I notice how actually at this step, the lowest weight in the table is vertex D, which means vertex D gets added next along the edge DA. Okay, so I bring in vertex D. Okay, so now D is part of the tree. I then update the table for the neighbors of D, which would be F and H, and they now become accessible with weights 10 and 5. And then the next thing I bring in is H. There we go. And so I update the neighbors of vertex H. That allows G to finally be accessible. Now notice that actually E is accessible from vertex H, but the edge from H to E has got weight 12. So E continues having weight 7, and its tree neighbor continues being B. Okay, so then I bring in vertex E, there it goes. And when I bring in vertex E, nothing needs to be updated because all of the neighbors of vertex E are already in the tree. Okay, so I bring in vertex G, and then I bring in vertex F. And the tree is now complete, and I finished the algorithm. I've finished performing Jarnı's algorithm on this graph. And what was great about that is at each step, what I choose is just the lowest weight vertex in the table. And then I already know what edge to use from that vertex because I just look at the tree neighbor of that vertex to figure it out. So what's interesting about this is I've pivoted the problem into finding the minimum weight vertex because I've assigned a weight to every vertex. And also, I have this table. Now, the weights in the table change, but at every step, I just want to find the minimum thing in this table, the minimum weight in this table. And vertices get added over time. That is, they become accessible, and their weights change over time. But at every step, the vertex that I want is the one with the minimum weight. And so I guess what I think is here, I could just use the table, and I can show pseudocode for that. So there it is. So I could just use the table, but maybe I could find a better data structure than a table to represent this. Okay, so here is the more advanced version of Jarnı's algorithm that uses the table. You give me some starting vertex v start, and then I set the weight of every vertex to infinity for all vertices v. I then go through the neighbors of my starting vertex, and I call this function. So this function I'm going to use to update the weight of a vertex when that is necessary. It's over here. And you can see that the way that it works is I give you the two endpoints of an edge. So here's a vertex, and here is its neighbor in the tree. So this would be v start, and this becomes u, and we'll call it v tree. So an edge from a vertex in the tree v to a vertex u outside the tree gets passed in like this. And then I just ask the question, is the weight from of this new edge from u to v tree less than the current weight of vertex u? In other words, am I able to access vertex u via a lower weight edge if I use v tree to get there? If the answer is yes, well then I've just found a better tree neighbor for vertex u. So I set the weight of vertex u to be the weight of the edge from u to v tree. The only reason that's on 2 lines is because I needed to keep it from wrapping in the pseudocode representation. And then I set the tree neighbor of vertex u to be my vertex v tree, this vertex that I came in on. Okay, so I update the vertex weight of every vertex next to my starting point. Then, as long as the size of tree vertices is less than the number of vertices in the graph, I choose the vertex with a minimum value of vertex weight of v. Now that looks like linear search. And then I add the corresponding edge to my tree. I add my vertex v to the tree vertices, and then I go through the neighbors of vertex v. I look at all the neighbors that aren't currently in the tree. That's significant, that if statement. It's going to make sure I can assert that we've got a good running time. And I update their weight based on the weight of the edge from v to u. And then that might mean that the tree neighbor of vertex u changes depending on if the edge from v to u has a lower weight than the current edge connecting vertex u to the tree. Okay, so the total number of calls to update vertex weight across the entire algorithm is actually, it should have highlighted this line too. The total number of calls to that is actually going to be this. And this is the usual argument we make with traversal algorithms, which is that I only call this once per edge, because I only call it if the other end of the edge is not already in the tree. So when one endpoint of an edge enters a tree, I call update vertex weight on that edge. I don't call it when the other endpoint enters the tree because I ignore those vertices in this loop. I don't have that if statement in this first loop here because at the beginning of the algorithm, nothing else is in the tree. So it makes sense the answer to the if condition would always be true. If I use linear search on line 9, well, then the total running time of the algorithm is going to actually just be v squared plus e. And so the reason that I say that is because the number of iterations of the outer loop here is going to be obviously the number, well, it's going to be the number of vertices all minus 1, so it'll be big theta of v. And then this is going to be linear search over the table, which has size, it's one entry per vertex, so it has size number of vertices. So that means that I run, this is v squared operations. The total number of iterations of this loop over all iterations of the inner loop is going to be the number of edges, or some multiple of that, so there could be a handshake lemma thing happening here. But overall, the total running time of the algorithm is going to be this. Because we know that we know that the number of edges is at most v squared, that actually means we're looking at big theta of v squared, which is better than what we had before. What we had before was v times e, which for a large number of edges could be as much as v cubed, and for a moderate number of edges, because we know that in a connected graph the number of edges is at least size of v minus 1. So this is definitely a larger running time than this. So we have improved over the basic version of Jarnı's algorithm or our earlier attempt, but we're still working with v squared. And the question is, can we do better? And really, it's line 9 that I want to blame for all of this. That is, this all taking this number of iterations, that sounds good to me. I mean, that does seem reasonable for a graph algorithm. However, doing linear search over a table to find the minimum value at each step does seem a bit wasteful, and we do know that there are data structures that can help us with this. In particular, I see that word minimum. I want to take the vertex with the minimum weight, add it to my tree. Wait a minute. Once I've added it, I want to delete it from the table, in a sense. Notice how back in our example, once a vertex was in the tree, we just pretended it wasn't in the table. It no longer participates in the comparison of weights. So what I want is I want a nice, clever data structure that allows me to find the minimum weight vertex at each step and then delete it from consideration. Remove the minimum weight vertex. And so basically that tells me I want a heap. So what I want is a remove min operation. I want to keep track of the weights of vertices using a heap because I know that at any given point I can ask for the thing in the heap with the minimum weight and I can delete it if I want to. There is one quirk though, which is that although I could use a heap to do this, I do have to change the weight of a vertex occasionally. That is, when a better tree neighbor becomes available, I have to change the vertex weight to accommodate that, and that could mean the vertex has to move around in the heap. And at that point, the vertex could already be in the heap. So I need some way of updating my heap as weights change. Notice how I'm not talking about priority queues here, I'm talking about heaps. And that's because this unconventional use case where I have to modify the key of something isn't one of our standard priority queue operations. So if I want to find some way of making it happen, I have to choose a data structure to implement my priority queue. And I guess I've decided to choose a heap. Why a heap? Well, because heaps have fast insert and remove min performance. So my idea is basically this. At the beginning of the algorithm, I create an empty heap. I add every vertex except my starting point to the heap with key infinity, because currently their distance, the weight of each vertex is infinity. Then, during my update vertex weight function, every time a vertex has an updated weight, I set the key of that vertex to W, the new weight. This means I need the ability to modify things in my heap, to move them around the heap because their key changes while they're already sitting inside the heap. And we haven't discussed that use case yet. So in our coverage of heaps, we just talked about inserting things and removing the minimum, the operations of the priority queue. Whereas this requires me to be able to modify something currently sitting in the middle of a heap. Nothing really changes beyond that. That is, on line 10, to get the next vertex, I call remove min. The rest of the algorithm is pretty much the same. And the remove min operation of a heap is log n, which means I can bring down the running time of this to be, well, this loop is still this number of iterations, but now, instead of being linear in the number of vertices, this operation would be log of the number of vertices. That's a pretty good improvement. So the question I guess we have to answer is, how do I do this? If I already have something in a heap, how do I adjust an existing key in the middle of a heap? And it turns out it's not so bad. It's a bit of a pain implementation-wise, but it's all doable and asymptotically doesn't change anything. So the standard heap operations, as we know, are insert and remove min. The problem is, if I look at one of the things in the middle of the heap, for example, I decide that this thing here shouldn't be 6, it should be 4, or it should be 1, well, I need some way of doing that. And it turns out it's not such a big deal. That is, I already have heap operations that help me with that. So I want the ability to efficiently modify the key associated with a particular vertex, even if it's already in the heap somewhere at some arbitrary place. So not the root, not in some predictable location like in the last leaf, just somewhere randomly in the middle of the heap. So suppose I change this to be something else. Can I restore the heap? And the answer is, as it turns out, yes. So if I were to change this 6 to be 100, okay, well, we know the old key was 6 and the new key is 100. And we know that in a heap, that means that if there's a problem, it's because 100 is too big, so it has to go downwards. So I would just run a bubble down operation. On the other hand, if I change 6 to be 2, we know that 2 is less than 6. So if a problem occurs, I mean, certainly that means 2 is still greater than, less than both of the things below it. It's still the minimum of the subheap rooted at that node. So that means if I change it to 2, the only problem could occur if 2 is less than the thing above it. So I would do a bubble up operation. So fortunately, if I adjust a key in the middle of a heap, there is a pretty easy strategy for how to fix the heap. If the new key is smaller, do a bubble up. If the new key is bigger, do a bubble down. Either of those takes log n time, and that's great, because that does mean I have to account for that time in my running time of this, but hopefully everything comes out in the wash. Hopefully that log n still helps me improve upon the linear time search I was doing previously around here in the algorithm. And it's also worth observing that actually we don't need this level of generality, because during Jarnı's algorithm, the only time I ever adjust a key is to make it smaller. I don't adjust keys when they get bigger. And so the only operation I need is actually a bubble up operation. But either way, it's log n. Okay, so the heap that I use is going to have the keys be the weight of each vertex, so I'll keep the table up so we can see that, but each node of my heap will also be tagged with the vertex itself, because of course, when I do a remove min and you give me back the number 10, that means nothing to me. I need some way of knowing which vertex we're talking about. So we've talked about before how in these data structures that organize data for collections, for example, like dictionaries and priority queues, we always have the option of tagging each of the elements of our collection with some arbitrary piece of data that rides along with the key. Here is a case where we definitely want to do that. So each node of my heap is tagged with the vertex that corresponds to that key, so that when I do a remove min, I know which vertex we're talking about. And so the keys of the heap are the weights of every vertex, and then I tag each node with the associated vertex, and I even have nodes in my heap that have weight infinity, and we can easily define a way of making that work, because, I mean, infinity is not itself a number, but we can treat it like one for the sake of it being larger, interpreted as being a larger value than any of the other finite keys. Now, there's also another complication that isn't, I'm not going to illustrate it directly here, but I need the ability to take an arbitrary vertex. So let's say in this example, I want to do vertex F or something. Notice how vertex F currently has weight 19. Well, there's going to be a point when vertex F has weight 4, I think. That is, I'm eventually going to, or maybe I'll set it to be weight 1. I mean, it makes sense. I will not bring in the edge 19. So there's going to come a point in the algorithm when I want to change the key of F to be something other than 19. And that's one thing in the table. I mean, there you go. It's now got weight 1. The problem is, how do I do that in the heap? Like, how do I find vertex F in the heap? The way I do this, I don't want to iterate over the heap because that's going to take linear time. So what I do is I maintain some mapping of vertices to heap locations. I could do this with an index because I likely implemented my heap with an array. So if I have an array-based heap, so here's index 1, here's index 2, here's index 3, then I would just store along with each vertex, so maybe tagging the vertex object itself, I would say vertex F is at index 2 inside of my heap. So I'd say it appears at index 2 inside my array-based heap. And then I make that way, if ever I want to change the key, I know exactly which index of the heap to modify. I can get that index in constant time. The trick is I have to be careful that when I write my bubble up and bubble down operations, that every time I move a vertex in the heap, I go and update the index associated with the vertex. Now this can all be done in constant time because I have a mapping between heap nodes and vertices, and I can maintain a mapping between vertices and heap nodes just by following to the vertex and updating things. But it is an extra step. So every time I move a vertex in the heap, I have to make sure I keep that mapping up to date. But it is possible to do that, and it can be done in constant time. Okay, so at this step, the root of the heap corresponds to vertex B, which means that B has the lowest weight, so I add the edge AB. I go look up the tree neighbor of B, it's vertex A, so I add the edge AB. Great. And then B gets deleted from the heap. After adding edge AB, I adjust the weights of the neighbors of vertex B. That would be vertex C and vertex E. As a result, C goes from having weight infinity to actually having weight 3. So C rises all the way to the top of the heap. A bubble up operation moves it all the way to the top. Great, because that is the next thing I want to bring in. So I bring in vertex C along edge BC. There it is. And then I update the weights of the neighbors of C. That would be vertex D and vertex E. And so before this, vertex D actually had weight infinity. Here's a really interesting case of a heap where, of course, this is the heap property is satisfied, but it's weird to see you actually have an infinity very close to the root here, whereas these finite numbers are buried all the way down in leaves. Okay, so I bring in vertex C. I update the neighbors of vertex C. That means vertex D is at the top of the heap. And there's a lot of machinery behind the scenes here. That is, to maintain all these mappings, I have a lot of different things mapping to each other. So the table would map to the heap, and the vertex object would map to both the table and the heap. The heap maps back to the vertex so that I can keep everything up to date and keep the mappings maintained. But all of that's constant time. And the heap is giving me what I need, which is access to the next vertex very quickly. And then over time, of course, the heap gets smaller and smaller, and eventually I've removed everything, and I have a minimum weight spanning tree. And fortunately for us, we already know that Jarnı's algorithm works, so we don't have to write a proof of correctness based on this version, because we know this is just an extension, an optimization of the version we started with. And in this graph, it turns out the total weight we ended up with was 25. Okay, so that's Jarnı's algorithm, and I guess we now have to, formally elaborate on the running time before we move on to our next algorithm, which is each iteration of the loop. I already sketched this out. It requires at most one remove min operation, which would be log in the number of vertices, because the heap contains at most the number of vertices in terms of nodes. Each call to updating the weight of the vertex, because of this thing, everything other than this line here in update vertex weight is constant. Each call, if it needs to do an adjustment, so in the worst case, requires log of the number of vertices time. And so the question now is, what is the total running time? We know that the loop here runs for this number of iterations, size of v minus 1. But then we've got this other loop that runs for, well, this is the number of iterations of this is the degree of the starting point. And so we have to do a little bit of annoying algebra here. And the number of calls to update vertex weight, as we discussed earlier, because of the way these two loops work, is at most this, so once per edge. So I have to do a bit of fumbling with algebra. It's not the worst. I'm going to use for this not size of v and size of e, because those are a bit messy. I'll just say n and m as per our convention. So the total running time would be, okay, this is that initial loop. So this thing here would be this loop. So that would be just setting up the initial state of everything. What I'll notice is that this is actually just sort of the same loop as this, minus an if statement. And that's the algebra I'm trying to do here. So the rest of it, the main loop is this term here. So for every vertex other than our starting point, we take log n time, there's the remove min operation, plus, in the worst case, the degree of that vertex times log n time for all the updates to its neighbors. So really what I want to do, and you can see the ultimate result here, I want to show that it's that. All I do is fiddle with terms a bit, so I split this up into two pieces. I notice that this loop here, well, the number of iterations will be n minus 1. Basically every vertex but the starting vertex. And so what I notice then is that if I just take this term and pull them apart, what I get is n minus 1 times log n, that ends up being here. And then once I've pulled this off into a separate, like a summation on its own, I realize that it's the same term as this. So I can combine this with this and merge them into one big summation. And I end up getting, I then pull the log n outside. So I end up getting this term goes down here, n minus 1 times log n, plus log n times the sum of the degree of all vertices of the graph. Okay, and that's the handshake lemma, so we know that's 2 times the number of edges. And so the complete running time expression ends up being this. We know, however, already that the number of edges is greater than or equal to the number of vertices minus 1, so asymptotically this just gets overwhelmed by this thing, and so the total running time is big theta of m log n, which in terms of the sizes of sets in the graph is this number of edges times log of the number of vertices. That's pretty good. So it's not linear, and unfortunately we're past the point where we can expect all of our graph algorithms to be linear, but it's damn close. I mean, log v is definitely a big step in the right direction from v times e. Now, it turns out we can actually do a little bit better than that. So we've got number of edges times log of the number of vertices using an exotic version of a heap called a Fibonacci heap. And I alluded to this back when we discussed heaps the first time, which we are not going to discuss. There is a version called a strict Fibonacci heap, which guarantees in all cases a worst case log n remove min operation and strangely constant time insertion and constant time key decrease operations. So using a Fibonacci heap instead of an ordinary heap, which by the way we call a binary heap, the old-fashioned style of heap we just used, if we use a Fibonacci heap, we can get the running time down to this. So number of edges plus v times log of v, which we can see might be beneficial in a graph with tons and tons of edges. So why aren't we going to talk about Fibonacci heaps? Okay, well, it's been 2 hours and I still have 2 algorithms left to cover, so have some mercy on me for that. But also because actually in practice, Fibonacci heaps are rather complicated. And so although we get these asymptotic guarantees, it may well be that a binary heap is pretty fast. So it's a case where, it's nice to have this result so we know certain things about asymptotic performance, but that doesn't necessarily mean that we're going to use this in practice. Okay, so that's Jarnı's algorithm, and Jarnı's algorithm is this vertex-centric approach, which starts with a small tree of one vertex and grows it outwards, keeping one tree at each step until the tree spans the entire graph. And that's one way of adapting the cut property to give us an algorithm. But it's not the only way, because I could, let's say, focus on edges instead of vertices. And that brings us to our next algorithm. So think about this. Consider this graph again, it's the same graph as earlier, and look at that edge CD. Notice that it is the lowest weight edge in the entire graph. And I argue that means it must be in a minimum weight spanning tree. And one way I could argue that is, being the lowest weight edge in the entire graph, if I choose any of its endpoints, so there's vertex C for example, clearly the lowest weight edge in the graph will be the minimum weight edge bridging one of its endpoints to the rest of the graph. And so the cut property does apply to that. Okay, so that means that this edge is in the graph, and this is something that's based on the weight of the edge, not specifically the vertices it's attached to. So I just considered the lowest weight edge and concluded it must be in the minimum weight spanning tree. So let's just add it. Suppose it's in the minimum weight spanning tree. Great, okay. Let's look at the edge with the second lowest weight. Okay, it's this edge here. Notice how this edge is far away. It is not directly connected to either of the two vertices I just looked at. And notice that this also must be in the minimum weight spanning tree, because as the second smallest weighted edge in the graph, if I look at, I don't know, like vertex B and everything joining vertex B to the rest of the graph, well, sure enough, this edge is the minimum weight bridging edge. So it also must be in a minimum weight spanning tree. And I realized that if I were to walk through edges in sorted order, I might be able to build the tree that way. In other words, suppose I put both of these two edges in the tree, and I consider the next edge up. That would be this edge here with weight 3. And I observe that, okay, well, this is a chunk of the tree already, then this edge must be the minimum weight edge bridging that to the rest of the graph. So it also must be in the tree. And so I could use that to iteratively build the tree in pieces by just adding one edge here or there. The key thing I have to prevent, if we think all the way back to the cut property construction theorem, is that I can't create cycles. I just want a set of edges that meet the criteria of the cut property but do not contain cycles. That's all I need. So my idea is, instead of trying to grow a tree from a single starting point, let's just focus on edges. Let's just iterate through edges in sorted order from lowest to highest weight and build a collection without cycles. And that collection, as long as I can verify that the cut property applies to each of those edges, I will eventually have a spanning tree, which will therefore be a minimum weight spanning tree. The next smallest edge is this one here, edge 3. AH is the minimum weight bridge between A and the rest of the graph, or alternatively between this little chunk of the tree and the rest of the graph. So the cut property confirms that it must be in the spanning tree that I'm building. Similarly for GH, that would be the edge, the fourth smallest edge. So we've got 1, 2, 3, and then there's 4. But now what about this edge here? So I consider this edge with weight 5. It's the next edge up in sorted order. And I conclude that if I think about what it connects this little chunk of the tree back to itself. So I have my tree in multiple pieces, but if I add edge 5, it will create a cycle. It connects two things that are already in the same piece of my tree. So I have to ignore it. So adding AB to our collection of edges would create a cycle, so we have no choice but to ignore it. There's no way it could be in the tree at this point. So I just keep going. What I could do here is I could keep track of, let's say we'll call them clusters. I sort of want to call them components. Maybe it's because the green outlines remind me of components. They are sort of components if we think of the edge collection as inducing a subgraph or something, but I don't want to worry about that. We'll call them clusters. So I could group all of the vertices into clusters and the groupings correspond to vertices that are already connected by edges I've chosen so far. So that the clusters I have right now are this cluster. This vertex is not connected to anything, so it's a cluster. Vertex E is its own cluster, and then C and D are in a cluster together. And so the question I'm then asking is, if I look at each edge in order by its weight, does the edge connect two different clusters, or is it within one cluster? So only edges that bridge between distinct clusters can be included without creating a cycle. But of course, this discussion of clusters and asking questions like, does this edge bridge between two separate clusters, that gives me a pretty powerful sense of deja vu. It sounds like I've landed exactly where I want to be right after the last lecture, which now seems like an eternity ago because that was at least 2 hours and 15 minutes ago. But what I seem to want here is something maybe like a union-find structure. Okay, so we'll keep going. The smallest weight edge that bridges two clusters is FG, so I add that edge to my collection, and of course that merges two clusters together because now F joins the cluster containing G. And this gives us an algorithm called Kruskal's algorithm. So Kruskal's algorithm iterates over all edges in ascending order of weight, and as it goes, it builds a collection of edges. And as it iterates over edges, if it finds an edge that bridges two distinct clusters, that edge gets added to the collection and the clusters get merged. Over time, I should expect the number of clusters goes down. Eventually, there's only one cluster, and at that point, I have a spanning tree. And each addition merges two clusters together, and that's how I know I'm making progress towards my result. So here's a sketch of Kruskal's algorithm, and it's a pretty basic version because there's a conditional that most people would add that I have not added. So first step, take all the edges of your graph and sort them into ascending order by their weights. And then I'll make a collection of edges here. I then iterate over my list of edges in ascending order, so each edge UV. I ask the question, are the two endpoints in separate clusters? And see if you can imagine a way of doing this using something we've learned about recently. If the answer is yes, then I add that edge to my tree edges and I merge those two clusters. And the idea here is I've actually already sort of admitted that we're going to want to keep track of the clusters separately just to avoid having to find them again every time we want to ask this question. Now, I mentioned this is a more basic implementation, so this is a good one to analyze, but people who implement it, including you, will probably add this extra if statement here, which is that you might not have to iterate through all of the edges in the graph to reach a state where only one cluster is left. And once only one cluster is left, the answer to this question will always be no, so you're sort of wasting your time by asking. So it makes sense if you discover at any moment in time that there's only one cluster left, then just return what you have. You're done. The algorithm is over. So this is an early return, and that means that it's nice and you should add it, but we're not going to worry about it for analysis because it's a best case situation, or it's a non-worst case situation. In the worst case, we may not get to only one cluster until the very last edge. So for analysis purposes, this is just a convenience. It's just an optimization. All right, let's try running Kruskal's algorithm all the way through. So I'm going to run it on this graph. We're going to start with every vertex in a cluster by itself. There we go. And at each step, we're going to choose the edge. We're going to walk through edges in ascending order of weight, and then choose to keep an edge if it bridges two distinct clusters. And maybe you can see in this that one of the brilliant aspects of this is the fact that it's pretty clear that the cut property is going to apply. Because if I simply choose my set S to be one of the clusters being merged, then I can apply the cut property directly to the edge, because we know that the edge bridges between a cluster and something else, the rest of the world. Okay, so notice that the clusters are outlined and every vertex is part of exactly one cluster. This is a problem that was pretty much just designed to be for a union-find structure. Okay, so the first edge in ascending order is CD. We already saw that, of course, gets added. The next edge is BH. We add that, then AH, then GH, and then we get to edge AB. But AB is entirely inside one cluster, so we ignore it. Okay, the edge FG bridges two clusters. We add that, then we get EF, then we get ED, and we're done. Notice that there are a bunch of other edges in the graph, and only once did we see an edge that bridged inside of one cluster. So only one edge had to be ignored. The rest of the edges that we don't need, we just never looked at. They all had high enough weights that we completed our tree before we even saw them. This is interesting, and that's one reason why you'd want to add that extra if statement when you implement the algorithm, because you could bail out before even seeing a lot of the different edges. It's also a hint, although this could just be a case like a well-chosen input or something, it's also a hint that Kruskal's algorithm exploits something that maybe is found in a lot of graphs, which is that it's generally speaking relatively unlikely that the highest weight edges are going to be in a minimum weight spanning tree, although it's possible. So for worst case purposes, we can't assume we're going to return early. Okay, so I'll do a flyover of this version as well. So here's that huge graph from earlier. Let's see what Kruskal's algorithm does on this. Pay special attention to how many times we see an edge that we have to ignore. Okay, so notice how the first few edges we consider, unsurprisingly, pretty much all of them we are able to perform merges because we've got lots of clusters, so the odds that an edge bridges inside the same cluster are relatively low. We keep going, and there we go. Here is an edge that is entirely inside of one cluster. Okay, too bad, so we have to discard this. Okay, that's the first one of these that we've seen, so we'll keep going. And we're done. We only saw one of them. There are lots of edges in this graph that we don't add to our spanning tree, but only once during Kruskal's algorithm did we actually see an edge that we had to ignore. That's a pretty good sign. That's a good sign that Kruskal's algorithm is exploiting an insight that's pretty meaningful. Now again, that doesn't mean that that applies in every case though. So notice that in both of these examples, we completed the spanning tree before many of those higher weight edges were even considered, and relatively few were rejected due to lying only in one of the clusters. Only in one cluster. Now, that said, of course, the exercise is go construct a worst-case input. So construct an input graph such that Kruskal's algorithm must consider every single edge, and the algorithm cannot terminate until after every edge has been considered, so it can't bail out early. Although that's nice if it happens, we can show that it's not something you can guarantee. That is, there are graphs where the maximum weight edge must be in the minimum weight spanning tree. We, in fact, saw one some ridiculous amount of time ago, like an hour and a half ago. I actually sketched one out. So the next question, of course, is what is the running time? And we have a pretty straightforward implementation here that is just conceptual. That is, it's got all this text like if the endpoints are in separate clusters. We could choose to implement this from first principles, but it would be pretty slow. And we're going to analyze the version without the early return because that does not change the worst case running time. So sorting the edges at the beginning, fortunately for us, we know all about sorting, and that's going to take this amount of time. So m log m, or number of edges log number of edges, for general edge-weighted graphs. So what's this qualifier for general edge-weighted graphs? So as I mentioned at the very beginning, if we assume that the edges of the graph are arbitrary numbers, well then the best way of sorting a collection of n arbitrary numbers, the best you can do is n log n time. However, if you know that all of your edge weights are, I don't know, like numbers between 1 and 5 or something, if you happen to be working with an application where the edge weights are highly restricted, maybe then you could bring in a specialized sorting algorithm like bucket sort or radix sort. And in that case, maybe you could do better for sorting the edges. And we'll see later that it turns out line 2 actually is the bottleneck. That is, the slowest part of the algorithm is the edge sorting. And therefore, there is an incentive, if you have that option, to find a better sorting algorithm. Now, the main loop pretty obviously runs for this number of iterations in the worst case. It just looks at every single edge, which means the only real unknowns are these two bits. That is, check if the endpoints of an edge are in separate clusters, and then do the merge. Okay, so the most basic way of doing that, I guess, would be to every single time you want to ask the question, is U in the same cluster as V, you could just do a traversal of your tree edges starting at vertex U. That is, you could just find the complete set of components induced by tree edges every single time. So basically what I'm saying is the clusters are just connected components of the subgraph induced by tree edges. That is, the bits of the tree that you have so far. If you want to decide if an edge is in one cluster versus bridging two, you could just do a traversal, okay? And that would require this amount of time. So of course it actually requires this, number of vertices plus number of edges. But we know already that in a connected graph, it's just going to be dominated by the number of edges, and so we call it big theta of E time. And then the merge operation, you could just do nothing, because you could just recompute the clusters every single time you ask the question. And so, okay, well, that means that I've got, this loop runs for that number of iterations. This if statement takes that amount of time to evaluate, and so I get a running time that's something like number of edges all squared, which isn't great, frankly. I mean, that is, we know that the number of edges could be as much as the number of vertices squared, so this could end up being as much as v to the fourth. On the other hand, we sort of already know where we're going with this. We know that we do actually have a ridiculously fast way of keeping track of clusters that won't require this. So this is pretty much an obvious use of a union find structure. So why don't we just go use a union find structure? Okay, so here it is. Create a new union find structure. Add every vertex as a cluster of size 1. For every edge, ask the question. If I ask for the representative of the cluster containing U and the representative of the cluster containing V, are they the same? If the answer is no, well then those two things are in separate clusters. So add the edge to my tree edges and then perform the union operation to merge them. We know already that, of course, the disjoint set forest is what we're talking about when we say union find structure, because it's so good at that job it has a monopoly. We also have already seen that the slides are being a bit modest here. We have seen that these two operations definitely require at most log n time. We've seen that. That was a whole thing. But we know that we definitely can get log n or better running time out of it. We know we can get way better than log n time, but we'd rather not revisit the mechanics of that. So we certainly know we can get log n time. And that means the time required by the main loop is therefore at most, notice the big O, because we do know some secrets about union find structures, the running time of the loop is at most E log V. But the running time of the algorithm is bottlenecked by this. So actually, it doesn't matter how much faster I can make my union find. Asymptotically, we already know the answer for how long this takes. It's E log E, which is the amount of time it takes in general to sort the list of edges. Okay, great. So that's why we had to prove that union find structures could give me log n performance, just to make sure that that was less than this, so that this can be the dominating term. Now, what this tells us, I guess, because we know that Jarnı's algorithm was E log V, this is supposed to be a way for us to understand that this, Kruskal's algorithm, is formally going to be asymptotically slower. Now, we should be careful with that because sorting itself might be very well optimized. So the constant time overhead of sorting might actually be quite a bit less than all of the constant time overhead associated with Jarnı's algorithm. But asymptotically, this seems to be telling us that Kruskal's algorithm is asymptotically a little bit slower. But not so, because it turns out that our old friend logarithm shenanigans can be used to show us that in fact E log E is the same as E log V asymptotically. Don't we just love logarithms? So I'll sketch that out. This is actually a proof, but it's not. It's mostly just fiddling with algebra. So on a connected graph, I claim that log base 2 of E is big theta of log of V, regardless of the value of E. And the reason for that is that we do know certain things about the number of edges on connected graphs. This isn't true in general for all graphs because there are graphs with 0 edges, and therefore you can't argue that 0 is log base 2 of V. But for a connected graph, you can. So remember that log x is an increasing function, and one thing we know about asymptotics is that if you know that f is big O of g, that means that since log is an increasing function, log of f is big O of log of g. Okay, so keep that in mind. We saw this earlier, that the number of edges of a connected graph is at most, or is at least the number of vertices minus 1, which of course is one way of, we can observe from that log of v is big O of log of e. Okay. We also know that e is less than v squared under all circumstances. So log of e is big O of log of v squared. And then we stare at v squared for a minute and we realize this is where the logarithm shenanigans happen. We see that squared and realize we can pull it out and we end up with this. So what we've actually shown is that log of e is big O of log of v. So we have that log of v is big O of log of e is big O of log of v, so they're both big theta of each other. Fair enough. Oh, great. Well, so although it feels to me as if this actually is trying to teach us something, the logarithm shenanigans allow us to conclude that in fact Jarnı's algorithm and Kruskal's algorithm by this analysis have the same asymptotic running time. Now, a couple of notes before we proceed from here. One really important thing to observe is, in the event that you can do sorting faster, everything changes. Because if you can sort this list of edges, let's say in linear time, the number of edges, well then the bottleneck is the running time of the loop. And I was using a pretty generous bound on that running time. That is, the loop, I said the loop is definitely no worse than E log V. But we know that union find operations are actually not log of the number of elements. They're actually something else, something weird. Which means we could show that if I can sort the edges faster, maybe the running time is way better than this. Something to think about. So we can conclude that Kruskal's algorithm is actually E log V, based on the logarithm shenanigans, and that is comparable to the version of Jarnı's algorithm that uses a traditional binary heap. On the other hand, if we were to implement Jarnı's algorithm with a Fibonacci heap, then we get V log V, and that is something that logarithm shenanigans can't get us out of. So that is, in that case, that would be definitively faster than Kruskal's algorithm in this formulation. And as I said, the main bottleneck here is actually the edge sorting, because obviously we know that union find is not big theta of log V once we've broken that all down. We saw that last time. That's all well and good, and that was a fun 2 hours and 30 minutes, but wait a minute, what did Borůvka do? So I've already discussed the fact that Borůvka was solving this problem in 1926, and that might have been a challenge because Borůvka was solving it before modern graph theory or, computers existed. And that by the time that Jarnı solved the problem in 1930, Borůvka clearly had already solved it because Jarnı's paper was presented as a response to Borůvka's paper. So what did Borůvka do? I really like Borůvka's algorithm, and that's why I saved it, because I figured that by this point in the lecture, I wouldn't have the same amount of patience for the other algorithms that I have for Borůvka's algorithm. So I want to describe Borůvka's algorithm. Variance, in practice, it turns out, if you are likely to implement a minimum weight spanning tree algorithm in practice, you probably would implement either Jarnı's algorithm, maybe more likely Kruskal's algorithm, or a more complicated algorithm, or one based on randomization. There are tons of algorithms for this task, many of which are faster than the ones we're talking about today, but are much more advanced. You are likely probably to use those in practice. But it's true that Borůvka was the inventor of the very first minimum weight spanning tree algorithm, and I love Borůvka's algorithm. The reason I like it is there's a certain sense of practicality behind it. That is, if my goal in this course was just to teach you an algorithm to solve every problem with the minimum amount of other work, which it obviously isn't for so many different reasons, if you look at the timestamp on the video, if that were my goal, I could teach you Borůvka's algorithm much faster than anything else. For Jarnı's algorithm, we had to come up with an instrumentation of a heap, an unusual way of working with heaps, as well as a whole bunch of other infrastructure to make it fast. For Kruskal's algorithm, well, it being fast depended on us already having had a whole lecture about union find structures. We need a lot of extra machinery to make those algorithms fast. What's brilliant to me about Borůvka's algorithm, and Borůvka probably wouldn't have known this because algorithms like DFS and BFS hadn't really been formalized the way they are now at that time, but it turns out that Borůvka's algorithm is competitive with the other two despite needing no extra bells and whistles. You can do it from basically first principles. That is, you can be sloppy about how you implement it, and it still comes out being really fast asymptotically. So Jarnı's algorithm was very vertex-centric. We start at one vertex and grow the tree outwards with one tree at a time. Kruskal's algorithm is very edge-centric. We work with all of the edges in order. That's the main thing that we use as our outer loop. Borůvka's algorithm can be thought of as sort of component-centric or cluster-centric. It does certain things that resemble Kruskal's algorithm, but it's definitely not edge-based. We don't iterate over all edges once. We use the edges as a way of considering what to do with each component, each cluster at each step. So Borůvka's algorithm, unlike Jarnı's algorithm, starts from one cluster per vertex. That is similar to Kruskal's algorithm. But unlike Kruskal's algorithm, it doesn't work with edges directly. It instead iterates over all the clusters and chooses an edge based on those. So we start with n clusters, so size of v clusters, each one with one vertex inside of it. And then the algorithm itself consists of a series of merge phases. Each merge phase consists of iterating over all clusters. And what we do is we look at each cluster, so I'll highlight the cluster we're currently working with in blue. We look at each cluster and we find the minimum weight edge leaving that cluster. So here that would be the edge 3. Okay, so we mark that edge off as that's one of the edges we're going to merge. And we do that for every cluster before we perform the merge. So I pick this edge, I go to the next cluster, that would be B. I choose the minimum weight edge leaving the cluster, that would be the edge with weight 2. Okay, I go to the cluster containing C, I choose the edge 1. I go to the cluster containing D, and actually I choose the same edge again. So the cluster C and the cluster D both choose the same edge. That's fine. Okay, I go to cluster E, I choose the edge 7. I go to cluster F, I choose the edge 6. I go to cluster G, I choose the edge 4. Okay, so now I'm done the merge phase. Oh, actually, sorry, I also do the cluster H, and I choose this edge that I'd already chosen before. And so it's fine if different clusters choose the same edge, and it makes sense that they would. For example, if you look here, the minimum weight edge exiting both of these clusters is the edge CD. So at the end of the merge phase, I've marked all of these edges as being ready for merging. And what I do is I add them all to my set of tree edges, and then I figure out what components I'm left with when I'm done. Okay, so I've added all those edges, and I still have more than one component, so I don't have a spanning tree. So then I run another merge phase. I just keep running merge phases until what I'm left with is one component. So I recompute the clusters, and I do the same thing again. Okay, here there are only two components, so I choose this edge as the minimum weight edge leaving the component, and then I choose this edge again as the minimum weight edge leaving this component. And then I have this edge ready, I perform the merge, I have one cluster left, and the algorithm is done. Total weight is 31. There it is. That's Borůvka's algorithm. So, as with our other two examples, let's do Borůvka's algorithm on this large graph. And I find this really fascinating, both because I think when you look at the example, you will feel like the algorithm is going to take longer. That is, it seems like it's doing a lot more work than Kruskal's algorithm especially. Kruskal's algorithm is very clean and streamlined. It just looks at a bunch of edges and performs merges. Here, I have to iterate over all my clusters, do a merge, iterate over them all again, do another merge. I think that's a reasonable critique to make. I think it's true that the algorithm seems to have a lot of steps. But what's interesting is to notice in a minute we're going to see the running time is still very fast. Okay, so our first merge phase, I'll just loop through, I'll just do a flyover of all the merges we do. Here we go, going through each component, choosing things to merge. And we perform our first merge. Here's the edges I'm adding at my first merge phase. There's the result. I've got these components. So I do another merge phase. There we go. All right, is that everything? One more. There are the edges I've chosen. And so I add those edges, and I'm done. It's just two merge phases. Even on this large graph, I still just do two merge phases. And at the beginning of the new merge phase, I notice that I only have one cluster, and so the spanning tree is done, and there it is, weight 101. Now, there's one important caveat. It's not really that big of a deal, but it's something you have to bear in mind. Consider this state here. So I have two components left, and all of the edges between them have weight 5. The issue is, in a graph where you might have edges without distinct weights, so where there could be two edges with the same weight, you need to be very clear about what strategy you use to pick the edge. So if the strategy is just choose some minimum weight bridging edge between, or minimum weight edge leaving this component, I could just choose this one because all of the edges have weight 5. So suppose I choose this edge here, okay? I go to the next component. There it is. And then I say choose a minimum weight edge leaving the component. So I choose this edge here. Uh-oh. Notice how once I actually do the merge, these two edges together are going to create a cycle. There are two different ways of joining the same two components. So that's a problem. But it turns out that's only because there was a tie. So if there was only one edge to choose, that is, let's say that this edge here had weight 1. Well, then this component would choose this edge, and this component would also choose the same edge. There wouldn't be a cycle. The only reason I had the problem was that there's ambiguity, and both components chose to act separately, and they happened to choose things that got in the way of the other component's choice. So all we need to do to fix that, and everything still works, and this does not add anything to the algorithm asymptotically, all we have to do to fix it is use a tie-breaking rule. So there's only ever one choice available. For me, I guess the easiest tie-breaking rule would be select the edge that is alphabetically smallest. So if we think about the 4 edges available here, they are AB, AG, EF, and FG. So if I write those all down and I take the one that comes first in the alphabetical ordering, it's going to be AB. So this component chooses edge AB, and then this component chooses edge AB, and everything's good. So all you have to make sure is that if there's a chance that edges don't have distinct weights, which is a chance you should reasonably consider, that when you see multiple edges, that you always compare them not just by their weight, but if there's a tie in their weight, you also compare them by some definitive tie-breaking rule, for example, choosing lexicographically smallest edges. So in this case, that would be edge AB. Okay, here is some pseudocode for Borůvka's algorithm. And as before, for the sake of discussing the algorithm, we can make this high-level version of the pseudocode. So we have a set of tree edges. I'll just have an infinite loop here so that I can end the loop whenever I choose in the middle. At each step, I go compute the connected components of the subgraph induced by tree edges. So with this vertex set and this set of edges, I go find the components. If there is only one of them, then I'm done. Otherwise, I loop through the components one by one, and we know already that it's very easy to compute the vertices in every component while we compute the components themselves. We can just make lists of them, so that can be done very quickly. And we also see this loop's running time is clearly just the number of vertices this is the number of components, but if I have to iterate over the vertices in each component, that's going to add up over the course of all iterations to the total number of vertices. So for every component, I just go into the component, I find the minimum weight edge with one endpoint in the component and one endpoint out, and then I add it to my set of tree edges. Now back to what I was saying a second ago. So this loop in total, if I iterate over every component, all the vertices in the component are in like a list together or something, then finding the minimum weight edge leaving the component, I just iterate over all those vertices and look at their neighbors. Which means if I think about it, well, first off, I iterate over every vertex exactly once per merge phase at most, and I iterate over every edge exactly once, or maybe twice, I guess once from each end. So it's similar to the analysis of a traversal algorithm. So what's the worst case running time of this basic implementation? Okay, well, if I want to recompute components from scratch, I could just do that with one of the various algorithms we know in linear time. Okay, until I think of a better idea, let's suppose we do that. That would be big O of E. So I mean, we know already that the V gets dominated by the E there. The minimum weight edge leaving a component, well, as I said, I could just iterate over all the vertices in the component and look at its neighbors. I have to use a tie-breaking rule, but that doesn't add any real complexity. That's just an extra if statement. The total time to find the minimum weight edge across all components would just be, again, linear in the number of vertices and edges, because each edge will be inspected at most twice, once from each end. And I have to iterate over all the vertices in the components, so that adds up over all components to be the total number of vertices. Okay, so I guess what I've said there is that basically, under the notation we've been using, this is just big O of E, and this whole thing is just big O of E. This entire loop here is just big O of E. Okay, so that means the inside of the outer loop is all just big O of E, or big theta of E. So now the question is, how many times does this loop run? How many merge phases are there? Testing whether a particular edge. So if I'm iterating over all the vertices in a component, asking the question about whether an edge leaves the component, that can be done in constant time. Because when I computed the components themselves, I could easily have tagged each vertex with its component identifier. So looking at the edge, I just ask whether the edge joins something in component I with something in component I. And if it doesn't, then it exits the component. So that can be done in constant time. So each iteration of the outer loop requires this amount of time, V plus E, which we know is actually just E because V is dominated by E. All that we need to figure out now is how long does the outer loop iterate? So how many iterations are there? So that's really just the question, how many merge phases occur in the worst case? Okay, so during each merge phase, I go find every component and I look at the edges leaving it and I add one of them to the spanning tree, which means, as a result, every component will be merged with at least one other component. So that is, there could be some components that actually get merged with like 3 other components because several components merge into it. But in general, every component gets merged with at least one thing. So I suppose you could think of, I don't know if this is necessarily the worst case, but you could have a graph where you've got a bunch of components and they just sort of get paired up. So the number of components gets cut in half, essentially. If there were this number of components at the beginning of the merge phase, that means that there have to be this number at the end of the merge phase. I start with n components in total. After the n, so I have n components, then I have n over 2 components after at most after the first merge phase, then n over 4, then n over 8, and of course I stop when I get to 1 component. And that means basically what I'm asking is how many times can I divide the number n by 2 until it equals 1? And that's the worst case, because again, we could be lucky and one merge phase could do the whole job for us. But in the worst case, the number of components at the end of a merge phase is half the number I started with, and that means the number of merge phases is at most log n, where n is the number of vertices. So what does that tell us? What that tells us is the total running time of the algorithm, even with the most sloppy implementation I could come up with, is actually already the correct running time, already the running time I wanted, the running time of Jarnı's algorithm with a regular heap and Kruskal's algorithm, even though we can see tons of opportunities for optimization here. That is, of course, instead of computing components from scratch, I could use a union find structure. And as far as finding minimum weight edges, there are maybe data structures that could help me with that as well. But I don't need to. even if I just do everything in the most sloppy way, just using fundamental graph algorithms, I am able, with Borůvka's algorithm, the first minimum weight spanning tree algorithm, I am actually able to get a running time that is competitive with the other two. The other two algorithms that we saw over the course of the last nearly 3 hours are actually pretty complicated and require a lot of infrastructure. That's a pretty big deal. No extra tricks were needed. The algorithm is efficient even if I just compute components via the most basic algorithm that we already saw, and I just find my minimum weight edges with linear search. So you got to hand it to Borůvka for that. So where does that leave us? We've seen 3 algorithms here for the minimum weight spanning tree problem, and all of them solve that problem in running time, which is about E times log V. And they all have a few advantages. Although I think in practice, this would be a good time for a timing experiment, but I sort of want to reserve the right to assign that as an exercise. But basically, my instinct is that it's likely that Kruskal's algorithm is going to be very clean and streamlined. And union fine structures aren't difficult to implement, so it probably isn't too tough to implement Kruskal's algorithm. If you had to implement such a thing, then Kruskal's algorithm probably would be a good choice that would produce a pretty fast implementation. The issue with Kruskal's algorithm is it is pretty sensitive to the number of edges. And that means in graphs that are relatively sparse, with very few edges, that's a good thing. In graphs that are relatively dense, that could mean Kruskal's algorithm is at a disadvantage. On the other hand, Jarnı's algorithm, especially if you use these really specialized data structures like Fibonacci heaps, you can get the running time down to this. So V log V plus E. So linear in the number of edges plus V log V, which means if your graphs are very dense, so E is large, maybe Jarnı's algorithm is a better choice because you don't have the same dependency on the number of edges that you have in Kruskal's algorithm. The problem is, as we saw, a lot of overhead is needed. There's a whole bunch of infrastructure required to get Jarnı's algorithm to run quickly, and although that is asymptotically nice, it is a lot of work. It's a lot of code that you have to write, but also a lot of extra constant time overhead and these complicated data structures, which means it wouldn't surprise me if even on dense graphs, it is going to be pretty slow. Now, Borůvka's algorithm asymptotically is competitive, and one of the advantages of it is that you can implement it very easily. That is, if you know graph algorithms, if you know traversals, you can pretty much do it. You don't need to learn anything else. However, in practice, it does turn out that although, yes, you can achieve with Borůvka's algorithm that running time, doing it the sloppy way, that is going to take a while. I mean, we already saw, for example, even for tasks like computing connected components, it's likely that doing that with a union fine structure is going to be faster than doing it with DFS or BFS. And so Borůvka's algorithm is likely to be slower in practice, despite it being asymptotically the same, because it carries a lot of overhead. On the other hand, it does have its benefits. So one of them is, notice how when I look at the different clusters in Borůvka's algorithm, it's way back. When I'm performing a merge phase, I'm looking at each cluster effectively independently. That is, each cluster independently is identifying the lowest weight edge, leaving it. Which means, if I'm working with massive graphs with tons and tons of clusters, that I suppose Borůvka's algorithm, because it sort of allows us to treat each cluster separately, could allow parallelization. And there are algorithms that exploit this to produce very quick parallel solutions to the minimum weight spanning tree problem. I don't recall the name off the top of my head, but they're no longer named after Borůvka because extra machinery is used to help instrument that parallelization. So Borůvka's algorithm was the first algorithm, the first solution to the problem. It came into being before any other algorithms did, and indeed before any programmable computers existed. And although it may not be the first choice for today for a typical use, it still has benefits, especially for things like parallel computing, and that parallel computing comes into play often when you have extremely massive inputs. And when your inputs are so massive, you might want to distribute the computation among multiple machines. Borůvka's algorithm can be especially powerful because there are very specific places in the algorithm where the various pieces you've put together get united at each step. In other words, a merge phase can be done in parallel, and then the end of the merge phase is where each of the threads has to join back up and share information. And that's pretty powerful. We don't have that benefit with Jarnı and Kruskal. So there it is, the minimum weight spanning tree problem, the first of our optimization-based graph algorithms. We're going to see a few more of them. I think for the next few, I'll split the lecture up into more pieces than this because this was a little bit excessive. And what we've seen here is that it's necessary to cover more than one algorithm for the task because there are multiple cases. There are different types of graphs we could consider, and in some cases, as we'll see in the next graph algorithms problem that we address in a couple of lectures, there are constraints that could exist on the problem that could dramatically affect which algorithm would work. We didn't see that so much here, but that also comes in as we see other optimization-based graph algorithms.